A visitor from beyond the solar system has just pulled off the seemingly impossible, and the whole planet got to watch. The interstellar object known as 3Y Atlas reached perihelion, its closest approach to the Sun, on October 29, 2025 at a distance of approximately 1.36 astronomical units from the Sun, or about 203 million kilometers. What makes this moment extraordinary is not only that 3I Atlas achieved this orbital milestone, but that every telescope on Earth, and in space, had the opportunity to witness what unfolded. It marked a grand juncture in humanity's gaze outward, where the universe revealed a rare trick, and we were watching. Before we start, smash the like and subscribe buttons for more updates. From the moment of its discovery on July 1, 2025 by the Asteroid Terrestrial Impact Last Alert System Atlas Telescope in Chile, 3I Atlas drew attention. Astronomers recognized its trajectory, speed, and origin as unmistakably interstellar. It came from beyond the gravitational hold of the Sun, hurtling into the inner solar system on a hyperbolic path with eccentricity greater than 6. As it descended toward the Sun, a chorus of observatories turned their lenses and detectors toward it, ground-based scopes tracking its motion, spaceborne instruments tracing its chemical fingerprint, and orbital platforms lining up to capture what happens when a wanderer from the galaxy plunges near our star. As 3I Atlas neared its closest solar encounter, the speed picked up dramatically. At perihelion, it was moving at its maximum velocity with respect to the Sun. The location of perihelion, between the orbits of Earth and Mars, placed it in a region where both solar radiation and solar wind exert powerful influence. Inside the inner solar system, the intensity of the Sun's heating, the pressure of its particles, and the flux of electromagnetic radiation all build to a crescendo. For any cometary body, this is a make-or-break moment. Sublimation of ices accelerates, dust and gas gush outward, and the structure of the object is stressed from all sides. For an interstellar body, this is doubly significant. The first time in many millennia, perhaps, that its surface has experienced such intense solar exposure. What we observed, therefore, was not simply a passive flyby, but an active transformation. The object's coma, the cloud of gas and dust enveloping it, brightened, the tail developed, the gas emissions changed composition and orientation, and the outgassing patterns evolved. Instruments aboard the James Webb Space Telescope captured a CO2-dominated gas coma with surprisingly high CO2-H2O ratio, hinting that 3Y Atlas's ices formed under atypical conditions compared to many comets in our solar system. At the same time, ground-based polarimetric studies revealed an unprecedented negative polarization branch, indicating that the dust in the coma has properties unlike most known cometary dust. From Earth's vantage point, however, the visibility of 3I Atlas during this crucial phase was uniquely challenging, yet every telescope capable of observing could still contribute. In late October, the object passed into conjunction with the Sun as seen from Earth, meaning it lay nearly behind the Sun and was difficult or impossible to observe from ground-based telescopes in many places. But satellite-based instruments, coronagraphs, and space telescopes were able to keep track, and when the object emerged again in November, it gave observers their first good look post-perihelion. Every observational platform that could was on alert. In a sense, the entire astronomical community turned its gaze as one to this event. The implications of this event ripple broadly. First, the fact that an interstellar object like 3Y Atlas could be detected with enough advance notice to deploy a full suite of observations marks a major milestone. Until now, only 2 other such objects had been identified, the intriguing spindly 1-9 Oumuamua in 2017 and the icy 2I/Borisov in 2019. 3I/Atlas' discovery, while still several astronomical units from the Sun, meant that routine and specialized telescopes alike had time to schedule observations, hone strategies, and observe over a longer arc. That gives us a deeper baseline for comparison and analysis than ever before for an object inbound from interstellar space. Second, perihelion is a natural stress test. Solar heating, enhanced radiation pressure, and intense particle environment all conspire to reshape an object's physical and chemical behavior when it's that close to the Sun. For 3I Atlas, the journey into and out of perihelion promises to reveal not only its composition but its structural resilience. In effect, the sun acts as both sculptor and interrogator. Many comets from the solar system disintegrate, fragment, or undergo dramatic evolution as they near the sun. For an interstellar object that has likely traveled eons through deep space, unknown thermal and physical histories are at play. The fact that every capable telescope had a front row seat to this transformation means we collect data across wavelengths, time, and instrumentation in a comprehensive way. Third, this event speaks to the universality of planetary system processes. If 3I Atlas formed around another star, potentially billions of years ago, and has traveled through the Milky Way to visit our neighborhood, then its chemistry and structure offer a direct sample of another system. By observing what happens when such a visitor experiences our sun's influence, we gain an analog of how comets in other systems might behave when subjected to stellar environments. That becomes especially powerful when comparisons are made with comets from our solar system. Similarities and differences in outgassing behavior, dust composition, tail formation, and changes during perihelion passage all become lenses through which to view planetary system diversity. Fourth, the fact that every telescope accessible was engaged sets an observational precedent. The coordination of observations across the globe, ground-based observatories, space telescopes, solar coronagraph instruments, and planetary orbiters, offers a template for how to study transient or one-time astronomical events. When an interstellar object passes through again, and eventually there will be others, this campaign will provide the blueprint for real-time, multi-platform monitoring. The sun-side perihelion phase in particular is a tricky observational window. Yet the fact we were able to maintain coverage despite the Earth-Sun object geometry shows how far observational coordination has come. Throughout the perihelion passage, the physical dynamics of 3Y Atlas were pushed to extremes. The heating from the sun's irradiation causes sublimation of ices, which then drive jets of gas and dust. That activity in turn reshapes the coma and tail morphology. The high outflow velocity of gas and dust under sunlight and solar wind results in dust tails that may be curved, segmented, or oriented in unexpected ways. Observers noted an emerging anti-tail feature, a dust tail that appears to point toward the sun rather than away, a geometric effect seen in comets, but under the unusual circumstances of an interstellar object that has a retrograde and low inclination orbit. Because the orbit of 3I Atlas is inclined only about 5 degrees relative to the ecliptic, but is retrograde at 175 degrees. The dynamics of how solar radiation and wind act on its particles differ from many prograde solar system comets. At perihelion, the solar elongation, the angle between the sun and the object as seen from Earth, reached values that made observational geometry particularly challenging. That means the object was effectively behind or near the sun from Earth's viewpoint, limiting visibility just when the effects of perihelion were most intense. Nevertheless, space observatories and coronagraphs recorded the dust and gas behavior, enabling scientists to examine how the object responded under solar heating in near real time. The fact that 3I Atlas reached its close approach while Earth's view was compromised underscores the importance of orbital assets and international coordination. Because the object is on a hyperbolic trajectory, once it passes perihelion and continues toward the outer solar system, it will not return. It is an interstellar visitor on a one-time pass. Thus, the moment of perihelion is the apex of the encounter. After this, the object's activity will quiet as it moves away from the sun. Its coma will fade, dust disperses, and observational opportunities decline. The fact that the full ensemble of telescopes position themselves for this apex means that the scientific harvest at perihelion will be the richest and most intense. The richness of the data collected during this perihelion isn't simply about capturing a pretty picture of a comet. It's about revealing internal composition, nucleus structure, activity drivers, dust properties, outgassing patterns, gas ratios, and morphological changes, all under solar stress, and all for an object that didn't form in our local environment. For example, the CO2-dominant coma suggests that 3I Atlas's nucleus may have original ices preserved in a state uncommon among solar system comets. The negative polarization branch indicates unique dust particle size distribution or surface texture. These details matter because they allow astrophysicists to infer formation conditions, thermal histories, and possibly the region of our galaxy from which the object came. Another significant implication is related to planetary defense and the monitoring of small bodies. While 3I Atlas posed no threat to Earth, its closest approach to Earth will be around 1.8 AU, or approximately 270 million kilometers. The ability to identify, track, and monitor such high-velocity, non-bound objects demonstrates the maturity of current survey systems and the readiness of international astronomy to respond. The Perihelion Passage and the Global Observational Campaign highlight how the community can mobilize when an unexpected interstellar visitor appears. It sends the message that if something significantly closer or more threatening were to approach, the infrastructure and coordination exist to observe, analyze, and respond. Moreover, 3I Atlas's Perihelion Passage opens new theoretical windows. Questions such as how long such objects have traveled through interstellar space, what level of solar exposure they have previously experienced, how their surfaces evolve, and how their dust and ice reservoirs respond to intense heating become accessible. The perihelion phase acts as a natural experiment, an ice-rich body from outside our system, suddenly exposed to the sun's full power, gives us a laboratory to test our models of ice sublimation, dust ejection, tail formation, and nucleus evolution in extreme conditions. The fact that this body came from elsewhere adds an extra dimension. How do objects formed around other stars behave when subjected to our sun's influence? Are they structurally similar? Do they devolatilize in the same way? The observations made at and just after perihelion will answer such questions. In practical terms, every telescope on Earth being able to see it or attempt to during perihelion is not just poetic, it's transformational. The phrase every telescope may be hyperbole in strict technical sense, but the meaning stands: ground-based arrays, robotic survey scopes, amateur equipment, space telescopes, solar observatories, planetary orbiters all contributed. The international astronomical community rallied around the event, generating a nearly continuous data stream across wavelengths, from optical and infrared to spectroscopy, polarimetry, and high-energy instruments. That holistic data set will outlast the event itself and fuel decades of research into interstellar small bodies. The fact that this event happened now is fortunate. The discovery-led time allowed preparation. The orbit brought it into a region of the inner solar system where multiple platforms could observe. The perihelion geometry, while challenging, did not preclude space assets, and the technology and coordination existed to take advantage. Future interstellar objects may arrive with less warning, less favorable geometry, or at times when observational infrastructure is less ready. 3I Atlas thus serves as a benchmark, a gold standard for how to observe and interpret such rare cosmic visitors. We are witnessing the solar system not as a closed system, but as one node in the vast web of the galaxy. When 3I Atlas reached perihelion, it told a story of a journey that began around another star, traversed the void of interstellar space, and now passed near our star. The fact that we could turn our telescopes and our minds toward it and see it behave under solar stress is remarkable. It reinforces the idea that celestial bodies are not strictly homegrown. Our cosmic neighborhood is porous. Extrasolar objects can visit, and when they do, we can watch them. At perihelion, the object's dynamics changed most rapidly. Solar heating intensified, sublimation increased, jets and dust plumes evolved, the coma expanded, and tail features began to reshape in response to the sun's wind and radiation. The raw energy input from the sun acts as an engine converting frozen volatiles into gas and dust, raising questions about how deep into the nucleus that heating penetrated, how much material was lost, how the surface morphology changed, and whether fractures or fragmentation occurred. For interstellar objects, which may have experienced little thermal processing for eons, this thermal shock could therefore be especially revealing. Observations from perihelion onward will allow scientists to measure the rate of dust production, analyze the composition of ejected materials, map how the coma changes over time, and see how tail morphology evolves as the object turns from inbound to outbound. Because the object passed through conjunction with the sun from Earth's viewpoint, the episodic nature of the observations underscores a key lesson. When geometry is bad, space assets pick up the slack. The fact that satellites and planetary orbiters captured data during the critical period means that the viewing limitations from Earth didn't stop the event from being observed. This demonstrates the necessity of multi-platform readiness and diversified observing capability. Even if ground telescopes cannot always see the object, space-based observatories still can. That every capable telescope on Earth and beyond had access to 3Y Atlas at Perihelion means the event wasn't partly missed. We have near-complete coverage of one of the rarest astronomical events we might witness. In terms of scientific legacy, the perihelion passage of 3I Atlas reaffirms that interstellar objects are not simply curiosity items, but are accessible laboratories. They allow us to test models of small body dynamics, formation, and evolution in new contexts. For instance, comparing the dust grain sizes and composition of 3I Atlas with those of solar system comets may reveal whether the processes of planet formation, ice retention, and volatile evolution around other stars produce similar outcomes, or whether significant diversity exists. The results from perihelion, jet behavior, coma composition, tail dynamics will feed into those analyses. From a philosophical standpoint, the event reminds us of our place in the galaxy. We like to think of the solar system as our domain, but objects like 3I Atlas remind us that we are part of a much larger galactic ecosystem. The fact that an object formed elsewhere traveled through the interstellar medium and ended up brushing past our star underscores how interconnected cosmic processes really are. And when every telescope watches, we become part of that connection. Observers and participants in a moment of cosmic exchange. The multispectral observations conducted at perihelion provide a multifaceted view. Optical imaging reveals tail morphology, infrared spectra reveal volatile composition, polarimetry reveals dust and surface texture, dynamical tracking reveals orbital mechanics and trajectories, and comparative studies place the object in context of both solar system comets and previous interstellar visitors. Because 3I Atlas was well placed for observation, the perihelion event will serve as a reference point for future studies. In short, it may become the benchmark against which we measure future interstellar small bodies. In sum, the moment when 3I Atlas reached perihelion is a turning point in our observational era. It is a rare cosmic wink, a visitor from the stars passing near our sun, showing off its behavior under solar stress, and doing so while observers around the world align their instruments to capture it. The data gathered promises to enrich our understanding of interstellar objects, planetary formation, cometary physics, and solar system dynamics. It demonstrates that when the universe offers such encounters, humanity's eyes, every telescope, every sensor, are ready and watching. The object known as 3I Atlas made its closest pass to the sun, and in doing so, took part in a cosmic ritual of transformation unlike any other we've ever witnessed. As it reached perihelion, the moment of maximum solar exposure, it entered an arena of extreme physics and chemistry. There it was subject to the full power of solar radiation, the relentless blast of the solar wind, and the intense tidal forces of our star. For an interstellar wanderer, born around another star and expelled into the vastness of the galaxy, this moment was a rare and final interaction with a star at such close quarters. From within that encounter arise a host of revelations about cosmic birthplaces, material survival, and the mechanics of small bodies under stress. As 3I Atlas moved inward, toward the inner reaches of our sun's domain, the timeline of its journey accelerated. The heating of its surface grew rapidly. Volatile ices that had slumbered for possibly billions of years now began to vaporize. Dust embedded and locked beneath layers of frost began to be liberated. Ejecta, gas and dust streamed from its surface, creating a dynamic coma that expanded outward and a tail whose morphology evolved in real time. The solar heat did more than intensify activity. It forced the object to reveal its inner structure, to expose hidden layers, and to display behaviors shaped in distant stellar nurseries long ago. This passage through the sun's domain became a transformative crucible for an object not of our solar system. In that heady moment of perihelion, one of the most intriguing processes was the change in dust emission and the tail's growth. The tail of 3I Atlas lengthened. Particles once loosely bound to the nucleus became vulnerable to radiation pressure and solar wind, and were swept away, forming elongated structures behind the object. Observations noted that the anti-tail, the portion that sometimes appears towards the sun under particular geometry, became visible. a telltale sign of dust-sized and distributed in unusual ways. This shift in tail geometry carries deep meaning. It reveals the size distribution of the dust, the velocity of ejection, and the interplay of forces acting on these particles once released. For a visitor from interstellar space, such behavior provides an unprecedented point of comparison to comets born in our own system. Another dimension of the story lies in the chemistry. The perihelion passage intensified the outgassing of volatile compounds: carbon dioxide, carbon monoxide, water vapor, and even more exotic species. Some of the early observations suggested a surprising dominance of carbon dioxide relative to water, hinting at a formation region far colder than the typical birth sites of solar system comets. The high CO2-H2O ratio suggests that 3Y Atlas may have condensed its ices in a distant, cold outer region in its original stellar system, perhaps much farther out than the snow line around its parent star. When the sun's warmth reached that frozen wanderer, conditions triggered the release of gases and dust in patterns not often seen in solar system comets, and that offers clues about remote protoplanetary disks and the environments around distant stars. The perihelion encounter also enabled scrutiny of the nucleus's physical integrity. Cometary nuclei can be fragile, often comprised of loosely bound ice, dust, and rock aggregates. Under intense solar heating, these bodies may fracture, fragment, or even disintegrate altogether. For 3I Atlas, rooted in a far-flung origin and possibly subjected to very long exposure to cosmic rays in deep space, this passage posed a test of survival. Did it hold together? Did the heating penetrate deep into its interior? Did structural weaknesses manifest as jets or breakup events? Observational records during and after perihelion place constraints on those questions. The fact that it survived its closest passage, maintaining coherence and continuing its outbound trajectory, speaks volumes about the resilience of such ancient wanderers. It opens the door to asking whether interstellar comet nuclei might be more robust than previously assumed, or whether we simply caught this one at a fortunate moment in its evolution. Beyond the physical and chemical transformations, the perihelion passage also offers insights into orbital dynamics under extreme conditions. As 3I Atlas accelerated toward its sun-skimming moment, its velocity peaked. The sun's gravity, combined with the object's hyperbolic speed and retrograde orbit, meant that the object experienced a steep change in potential and kinetic energy. This dramatic trajectory through the inner solar system creates a short window where non-gravitational forces such as outgassing jets can perturb motion in measurable ways. When jets erupt and dust is expelled asymmetrically, the resulting momentum transfer can alter the comet's path subtly, adding nuance to its dynamic model. Thus, perihelion is not just a heating event, but a moment when the interplay of forces is richest, and for 3I Atlas, the data collected allows a rare study of how interstellar bodies move and evolve when nudged by forces beyond gravity alone. The broader context of the perihelion of 3Y Atlas includes what it says about the populations of such objects. It joins the very small set of confirmed interstellar bodies. Its passage through the inner solar system is effectively a once-in-a-lifetime event for the object itself, and perhaps a rare event for us to observe in such a favorable geometry. The fact it made perihelion between Earth and Mars means the sun's influence was strong but not so close as to destroy the object outright. This sweet spot allowed survival but intense exposure. That circumstance ensures that the moment of perihelion becomes a benchmark, a case study for how interstellar comets behave when they plunge deeper into a star's domain. Future discoveries of extrasolar small bodies will refer back to this event as a comparative baseline. In addition, the perihelion passage of 3Y Atlas underscores the story of cosmic travel and endurance. Here is an object that has likely drifted through the galaxy for billions of years, perhaps untouched by major heating events, and perhaps passing through cold interstellar space, dormant and unaltered. Then it approaches a star, our sun, and in a matter of weeks or months, it experiences dramatic transformation. That transformation is a microcosm of the life cycle of small bodies: formation in a disk, ejection into the galaxy, drift through interstellar medium, encounter with another star, heating, erosion, and eventual fade into darkness as it departs. In this sense, the perihelion of 3I Atlas is not just an isolated event, but a chapter in the story of matter in the galaxy and how far it can travel and still reveal itself. The event also prompts reflection on how matter from one star system may end up in another. The fact that 3I Atlas formed elsewhere and now interacts with our Sun suggests that the flow of small bodies between stellar systems is real. The perihelion moment is tangible evidence of that exchange. If such wanderers visit other systems, they can carry with them the material fingerprint of distant worlds and processes. During perihelion, that fingerprint is revealed as the object responds to solar input. The composition of ices, dust grains, and structural properties all speak to formation in another environment. By studying how 3I Atlas responded to the Sun's influence, science gains a richer understanding of how materials migrate across yards of space and epochs of time. Moreover, the perihelion moment lays groundwork for refining models of comet activity in extreme environments. Solar comets have long been studied to understand how heating, radiation, and sublimation drive dust and gas release. But those models are calibrated on objects that formed relatively nearby and have experienced repeated solar passes. Interstellar objects like 3I Atlas break that mold because they likely visited a star only once or very few times and have not been processed by multiple perihelion passages. This means their volatile inventories, dust properties, and structural features could be closer to primordial conditions. The data gathered during perihelion thus feeds into the fundamental science of comet evolution, volatile retention, surface aging, and space weathering in a novel way. The speed of 3I Atlas at perihelion is also a matter of interest. The hyperbolic velocity, the already high inbound speed, and the acceleration into the Sun's well mean that the object is moving through the solar system on quite different temporal scales than typical bound comets. That in turn affects how rapidly solar heating acts, how quickly gas and dust are liberating, and how the morphology of the tail evolves. The compressed time frame of perihelion exposure offers a sharp contrast to the more gentle visits of typical solar system comets. The rapid dynamics mean that some processes, such as fast and perhaps sudden increases in activity, fragmentation, or changes in the dust-gas ratio, may play out on timescales that challenge existing observational plans. Fortunately, in the case of 3I Atlas, scientists were on alert and captured many details during that swift perihelion encounter. Another implication of the perihelion passage is the special window it provides for comparing remote sensing data across wavelengths. Observations during perihelion took advantage of infrared, optical, ultraviolet, and spectroscopic instruments, expanding the palette of what we can know about the object. The intense solar input at perihelion makes the comet brighter in gas and dust emissions, enabling detection of rarer species or weaker signals that might otherwise remain hidden. For a body that came from outside our system, this multi-wavelength scrutiny during closest approach is invaluable. It allows researchers to ask if the composition, dust texture, or emission behavior diverges significantly from comets of solar origin, and perihelion is the finest moment to make those comparisons. The survival or disruption of 3I Atlas through perihelion also branches into the discussion of small body mechanics under extreme conditions. For instance, the heating gradient from the surface inward, the ability of dust layers to insulate ice beneath, the role of jetting in altering spin states, or the potential for structural failure interiorly become pressing questions. If the object had fragmented, we would have seen a chain of smaller objects and altered dust emission patterns. The fact that a coherent object emerged means that its internal structure may be comparatively strong. That in turn may hint at its origin. Perhaps it consolidated under different conditions or endured different thermal histories than solar system comets. In this way, perihelion is a moment of cosmic stress testing for an alien-born object. The geometry of the encounter, too, is noteworthy, because 3I Atlas's perihelion lay between Earth and Mars, and because the viewing geometry was challenging for ground-based telescopes often close to the Sun from Earth's point of view, the data obtained must be interpreted carefully. The period around perihelion included a solar conjunction phase, where the object was nearly behind the Sun as seen from Earth, making continuous observation difficult from ground observatories. Yet despite that complication, telescopes both on Earth and in space contributed. The very fact that it achieved perihelion within reach of multiple platforms, and that the community coordinated to capture that moment, reflects how modern astronomy can respond to fleeting opportunities. The geometry forced constraints, but also offered unique vantage points. Different observatories caught complementary data, timing was tight, and the perihelion moment became a triumph of coordination and preparedness. In meeting the Sun at its closest approach, 3I Atlas laid bare its history. The surface composition, dust grain characteristics, and outgassing patterns all combine into a de facto archive of its long journey. The perihelion passage essentially peeled back layers of cosmic time. It revealed how an object formed within the swirling gas and dust around another star, how it survived expulsion, interstellar drift, and then encountered a star again. The moment of perihelion was the juncture at which we could ask not just, what is this object like, but what can it tell us about the history of matter beyond our solar system? Its passage through the Sun's embrace is a window into distant star systems, offering roughly analogous data to meteorite studies on Earth, but on a far grander scale. At the heart of the value is the notion of comparative planetology. Planets, asteroids, and comets in our solar system are the product of our star's specific environment. When we see a body like 3I Atlas approach our Sun, we are testing how a foreign body responds to familiar solar conditions. The perihelion passage is the stage where this comparison is most vivid. Do the mechanisms of outgassing, dust ejection, tail formation, and structural response follow the same physics? Or do they diverge in meaningful ways? The evidence from 3I Atlas suggests some divergence. For example, the tail morphology, the dust size distribution, and the composition hint at difference. Those differences at perihelion feed into larger questions. How varied are planetary systems in the galaxy? How do their small bodies compare to ours? And how universal are the processes we use to classify comets and rocks? The event also underscores the philosophical dimension, that the Sun is not isolated. Even as our star dominates our local system, it is part of a larger cosmos which sometimes sends travelers through its neighborhood. The perihelion of 3I Atlas reminds us that our solar system is akin to a cosmic crossroads through which interstellar wayfarers pass, that such a visitor can plunge toward the Sun, experience its full force, and then continue outward is a humbling reminder of the continuity of astronomical time and space. During perihelion, we were able to witness not just a comet, but a messenger from another system, with behavior inscribed across its coma and tail, dust and gas. It reinforces that when we look upward, we are seeing not only our own Sun's children, but cosmic visitors too. The perihelion event of 3Y Atlas sets the stage for future observational campaigns of interstellar visitors. While the aftermath of the passage will yield long-term data, the perihelion itself becomes a milestone. We now know that an interstellar comet can be caught, observed, and studied at its moment of closest solar approach. The strategies refined during this encounter, from scheduling across worldwide observatories, coordinating multi-wavelength instruments, managing phase angles and solar conjunctions, leveraging space assets, all emerge from the perihelion experience. It becomes a proof of principle. When an interstellar object approaches and reaches perihelion, scientists can be ready, telescopes can respond, and rich data can be obtained. As the Sun rewrites the visitor's surface, dust trails stretch outward, and gases escape into space. The perihelion of 3I Atlas becomes a landmark moment in interstellar science. The perihelion of 3I Atlas was not just a close pass. It was a moment of high drama, a demonstration of the cosmic ballet of formation and destruction, of travel and transformation. The object's passage through the Sun's inner domain provided a rare microscope into processes both fundamental and exotic. It allowed us to witness how materials formed in a distant star system respond to intense solar heating, how ancient ices behave under starlight after perhaps billions of years of cold dormancy, and how dust and gas liberated in that instant carry signatures of origin and evolution. The Sun's touch changed the object, and in turn, our eyes captured that change. That close passage between Sun and visitor will echo in the scientific record as one of the greatest opportunities to glimpse the deep history of our galaxy, written in the fleeting moment when 3I Atlas came closest to our star. The journey of 3I Atlas did more than simply bring an interstellar visitor into the inner region of our solar system. It brought a profound shift in how we conceive of small body science, planetary system origins, and the dynamics of the galaxy at large. As it carved its hyperbolic path past the sun and executed its perihelion passage, the object wove together threads of chemistry, motion, structure, and cosmic provenance in a tapestry of meaning that reaches far beyond a passing comet. By the time 3I Atlas approached perihelion, it had already revealed hints of exceptional behavior, activity at large distances, unusual ratios of gases in its coma, dust and tail features diverging from expectations. For example, measurements of hydroxyl emissions indicated active water outgassing even when it was still relatively distant from the sun. That early activity suggested that the mechanisms driving dust and gas release on this object may depart from the familiar models built on solar system comets. In effect, by the time it reached its closest solar approach, 3I Atlas carried with it the question of how interstellar comets differ not only in origin but in response to heating and solar interaction. As perihelion was reached, the object's environment shifted swiftly. The sun's radiant energy, the pressure of solar photons, and the outward blowing solar wind combined to create an extreme environment. For a body coming from interstellar space, one that likely had a cold, quiescent history, this represented a dramatic phase change. What had been preserved ice, mixed dust, and rock now faced sudden exposure. The outflow of gas and dust increased, jets might have formed, the dust tail stretched and curved under the interplay of forces, and the coma expanded. Observations from multiple platforms captured the evolution of the coma and tail morphology, with images showing the growing tail and expanding dust cloud. Because the perihelion region lies between the orbits of Earth and Mars in this case, 3Y Atlas's motion through the sun's inner domain allowed scientists to probe how materials with exotic origin respond under familiar stellar forcing. The change in solar heating as the distance to the sun shrank is dramatic. The object's temperature rises, sublimation increases, and dust liberation accelerates. In that interval, the nucleus structure is stressed, its volatile inventory is revealed, and its dust grain release is set into motion. For an interstellar object which may have been thermally dormant for eons, the heating profile, the onset of activity, and the residual changes post-perihelion all carry clues about how long the object remained in deep space and how its surface materials behaved under extreme cold. A particularly compelling aspect of the perihelion passage lies in how the dust behaves and how the tail is formed. For comets, dust grains of many sizes are liberated during outgassing. The larger grains remain near the nucleus longer, while smaller grains are pushed farther by radiation pressure, forming the characteristic tail. For 3 Atlas, observations implied a higher than expected dust production at large heliocentric distances, hinting at either a high volatile fraction or a surface with unusual dust-binding strength. The tail geometry, when observed at perihelion and shortly thereafter, showed features consistent with larger dust ejection velocities and possibly different size distributions. That means the dust behavior is a key diagnostic of the nucleus's composition, structure, and history. In addition, the coma's chemical fingerprint underwent transformation during and at perihelion. Prior to perihelion, spectroscopic work had already suggested a high carbon dioxide to water ratio, a feature that raised questions about condensation conditions in the object's birthplace. At perihelion, when the sun's influence is maximal, further volatile species become accessible for sublimation and emission. The relative abundances of CO2, Colorado, H2O, and trace molecules such as CN or OH change with solar heating, allowing scientists to infer how deep the heat penetrates and how quickly the object's volatile inventory is depleted or exposed. Because 3I Atlas came from outside the solar system and had arguably not been heavily processed by prior star passes, its volatile inventory may contain relatively pristine material, and the perihelion passage acts as a reveal of that inventory. The dynamics of the orbit itself carry their own implications. With an extreme hyperbolic trajectory, 3I Atlas is not gravitationally bound to the sun and will depart the solar system. That means the perihelion passage is a singular event, its closest sun encounter and the moment at which solar forcing is greatest. For scientists, that makes the perihelion phase a high-stakes window, one time to observe how this visitor behaves under maximal solar influence. Because non-gravitational forces such as outgassing jets may influence its trajectory, the perihelion region also gives insight into how small body motion for interstellar objects differs from typical solar system comets, where repeated perihelion passes and solar heating histories produce known effects. The perturbation of the trajectory due to mass loss, dust ejection asymmetries, and solar wind pressure can be assessed, and perihelion is when those effects are most measurable. One of the deeper implications of the perihelion event concerns the inventory of interstellar small bodies and the story of planetary system evolution. If 3I Atlas formed around another star and then was ejected into interstellar space and traveled for billions of years, its composition, structure, and response to solar heating tell us about that distant star system's protoplanetary environment. When it undergoes perihelion passage near the Sun, we effectively subject it to a known forcing and observe its behavior. Then we can ask, does it behave like our comets? Where does it differ? If there are systematic differences, that suggests that planetary systems produce small body populations with different volatile and dust characteristics than our own. The perihelion passage thus becomes a comparative experiment between solar and extrasolar materials. The perihelion of 3I Atlas also serves as a proof of observational readiness for such rare events. Because the object was detected well in advance of perihelion and global observatories' planned campaigns, the perihelion moment offered maximal data collection. Multiple spacecraft, ground telescopes, and survey instruments aligned to record its approach, passage, and egress. That matters because interstellar visitors may be detected later or under less favorable geometry. The fact that 3I Atlas's perihelion occurred in a time window where observatories could track it amplifies the value of the data. The perihelion passage marks not just a singular physical event, but a logistical and technical milestone in how we observe, coordinate, and analyze transient one-off cosmic interactions. In the region of perihelion, thermal modeling of the object becomes particularly rich. The heating of the nucleus surface, the thermal conduction into the interior, the lag between heating and sublimation, the formation of cracks or vents, and the evolution of the dust mantle are all processes activated in full force. For 3I Atlas, modeling these effects allows scientists to estimate the thickness of insulating dust layers, the porosity of the nucleus, the degree of compaction, and the fate of volatile reservoirs. Since this body may have had minimal solar exposure before, the differences in mantle development, dust crust evolution, and volatile depletion in previous passes are minimal, giving a near-pristine baseline. Consequently, the perihelion passage is a rare laboratory of the first exposure kind, revealing processes that comets in our solar system may have experienced many times before. The observational geometry during perihelion presented special challenges, and with that, special opportunities. Because the object passed into solar conjunction relative to Earth, many ground-based observatories lost direct sight, yet spaceborne assets and solar instruments filled the gap. That means that the data from perihelion is less fragmented than might otherwise occur for a faint, fast-moving object. The result is a more continuous picture of how the coma, tail, and nucleus behavior evolved during the closest approach. The alignment also permits different phase angles, allowing polarimetric and scattering studies to probe the dust grain properties under varying illumination geometries. Thus, perihelion offers both the intense stimuli and the high-fidelity observational windows needed for deep insight. From a material science and planetary science perspective, the perihelion event of 3I Atlas allows insight into volatile retention over cosmic time. If a body forged in another star system spent billions of years traversing interstellar space, exposed to cosmic rays, micrometeoroid bombardment, perhaps collisions and thermal extremes, how much of its ices and dust remain unaltered until this sun encounter? During perihelion, when those ices begin to sublimate and dust release occurs, the measured mass loss, gas composition, and dust size distribution become direct probes of how well such objects endure and what signatures of aging they carry. For example, if the water to CO2 ratio is high, or if dust grain sizes remain large, it may indicate minimal processing. If instead we see a devolatilized margin or depleted near surface layers, that indicates long exposure. Perihelion then becomes the moment when the preserved and the processed meet, and we observe the interaction. The tail morphology of 3I Atlas near perihelion also carries significance for solar and heliospheric science. As dust and gas are ejected, they interact with the solar wind and the sun's magnetic field. The ion tail can carry charged particles, and the dust tail is shaped by the radiation pressure and solar wind drag. For an interstellar object, the composition and mass flux of these ejections may differ, meaning that the resulting tail structures can challenge or expand models built on solar system comets. During perihelion, when mass flux is highest and solar wind interaction is most intense, the observational data from 3I Atlas lets heliophysicists and comet scientists refine how small bodies interact with the sun's extended environment. The perihelion thus connects comet science with solar wind and magnetospheric science in a very direct way. Consider also the implications for the inventory of material exchange between stars. If interstellar objects like 3I Atlas can enter the solar system and undergo perihelion interactions, they may deposit dust and gas, albeit minutely, into our heliosphere. The outgassing at perihelion injects material that originates in other star systems into our solar wind environment. While the amounts are tiny, each interstellar visitor is a messenger of material exchange in the galaxy. The perihelion passage of 3I Atlas demonstrates that such interactions are real, and that material from distant star systems can be processed in our neighborhood. It broadens the scope of solar system science to include galactic intersystem dynamics. Another interesting facet arises from the size and speed of the object as it approached perihelion. With an inbound velocity higher than previous interstellar visitors, and a nucleus size estimates covering a wide range, perhaps hundreds of meters up to kilometers, the physical scaling of processes at perihelion differs. Faster speed means less time spent near the sun's intense heating zone. Smaller size means faster thermal response and perhaps quicker exhaustion of near-surface volatiles. At perihelion, the interplay of size, speed, and solar distance results in a specific profile of thermal and physical evolution that may be quite different from the comets more slowly processed in our system. The perihelion moment becomes a unique case study of how these factors combine for a visitor from afar. In addition, the perihelion event sharpens our understanding of the interstellar object population's origin and age. If we measure the outgassing rates, volatile abundances, dust grain size distribution, and structural resilience of 3I Atlas during perihelion, we can infer its likely age, its origin environment, and how long it has been drifting. For example, if the volatile inventory is still high, perhaps it was ejected relatively recently. If it is depleted, perhaps it spent vast time in deep space. The perihelion passage is when these inferences receive their strongest empirical support. In that sense, 3I Atlas's perihelion moment is a forensic reading of its cosmic biography. The moment also prompts reflection on how we classify small bodies. The encounter of 3I Atlas at perihelion confronts us with an object that is not simply a comet like any other, nor solely an asteroid, nor purely interstellar debris. It is a hybrid in many respects: exotic origin, similar appearance to a comet, unfamiliar dynamic history. The perihelion passage reveals behaviors both familiar and strange. By observing under solar forcing, we bring such objects into the realm of comparative morphology and chemistry. Thus, perihelion acts as a classification touchstone, the moment when physical behavior under known conditions tests whether our taxonomies are sufficiently broad. The perihelion of 3I Atlas stands as a limit case. It is the closest solar encounter that this object will ever have with our star, the peak of solar influence on it, the moment when its activity and evolution are most extreme. After perihelion, cooling, decline of activity, fading tail, and coma mark the departure phase. From the standpoint of physical processes, everything pre-perihelion and post-perihelion is measured relative to this apex. The data collected during perihelion will form the reference for all subsequent analysis. In effect, the perihelion moment is the apex of revelation, when the object yielded its secrets at maximum solar pressure and offered the richest set of observational constraints. In moving past perihelion, the time behavior of 3I Atlas will continue to be informative, but the perihelion event itself remains the focal point. It is the time when structure, chemistry, dynamics, outgassing, and tail formation all peaked and synchronized under solar forcing. For the scientific community, the data from just before, during, and after perihelion provide a continuous thread of change, an empirical record of how an interstellar object behaves in the closest stellar approach it will ever experience. That record will be referenced in years to come, not just as another comet pass, but as the benchmark of interstellar small-body solar encounter. In the grand cosmic scheme, the perihelion passage of 3Y Atlas underscores that stars are not isolated but embedded in a galaxy where small bodies travel between systems, where planetary system formation ejects material that eventually visits neighbors, and where our sun is merely one host to dynamic influx and exchange. Through perihelion, 3I Atlas bridged star systems, brought alien matter into the sun's environment, and demonstrated that interstellar small bodies are not only real but accessible to direct observation. The perihelion event thus becomes more than a pass. It becomes a statement about our place in the galaxy, about cross-system exchange of matter, and about the continuity of cosmic processes. In short, the perihelion of 3I Atlas is the moment of greatest consequence for the object and for our observational vantage. It is the moment when alien material met our star at the closest practical distance it would see, when solar forcing pulled out the hidden composition, when dust and gas were liberated into the heliosphere, and when we, with our telescopes all aligned, captured the story. The insights gleaned during that passage will ripple across comet science, planetary formation theory, solar physics, and galactic astronomy for decades. The world watched, the telescopes turned, and at perihelion, 3I Atlas did the impossible. It brought a piece of another star system into our direct view, under our sun's light. When 3I Atlas reached the heart of its journey, the very closest approach to the sun, it became a nexus of physical processes, observational triumphs, and profound questions about the fabric of the cosmos. Every motion, every plume of dust, and every faint spectral line carried messages from a distant corner of the galaxy, written in ice and dust and illuminated by the brilliance of our own star. The event was not simply an astronomical observation, but a grand experiment, one that unfolded in real time with all the universe as its laboratory. At perihelion, the solar radiation bathing 3I Atlas exceeded anything it had experienced since its birth. The energy input increased by orders of magnitude as the inverse square law of sunlight intensified. Within hours, the surface temperature soared, driving rapid sublimation of volatiles. The once quiet nucleus, perhaps dormant for millions of years, awoke violently. Jets of gas erupted from vents in its crust, forming geyser-like plumes that vented material into space. As these jets burst forth, the nucleus responded like a living organism, spinning and vibrating slightly as reaction forces altered its rotation. Observers recorded minute but measurable changes in the object's light curve, oscillations that suggested the spin state was indeed changing under the stress of jetting. Such a detail might seem minor, but for scientists it spoke volumes. The sun's energy was actively reshaping the object's motion, sculpting both its appearance and its destiny. The perihelion moment also brought a unique kind of color. Photometric observations revealed that the coma, the glowing envelope surrounding the nucleus, shifted its spectral properties as the heating intensified. In visible light, it brightened sharply, but in the infrared, subtle patterns emerged, betraying the release of molecules like CO, CO2, NH3, and possibly CH4. These molecules, driven from the depths of the nucleus, expanded into space and were ionized by ultraviolet radiation, forming a bluish ion tail that extended for millions of kilometers. Space-based instruments traced these emissions, mapping the composition of the escaping gas. This allowed astronomers to deduce the thermal gradients within the nucleus, the relative depths of ice layers, the porosity of the crust, and the order in which volatiles were liberated. Every molecule released was a clue to a history far older than our sun itself. The sun's influence, however, was not purely thermal. The solar wind, a stream of charged particles moving at hundreds of kilometers per second, engaged the object in a complex electromagnetic dance. Charged ions in the tail responded to magnetic fields, bending, twisting, and sometimes breaking into filaments as the interplanetary magnetic field fluctuated. For heliophysicists, this was an unparalleled experiment. An interstellar object interacting directly with the sun's plasma environment provided data on how alien dust and gas respond to our star's fields. By comparing those effects with known comets, scientists could test whether the composition of dust and plasma from another stellar system behaves differently in a magnetized solar wind. Early analyses showed that the ion tail's fine structure hinted at a higher ionization efficiency, possibly due to unusual chemical species or grain charging properties. This offered the first empirical insight into how extrasolar matter couples to stellar magnetic forces. The geometry of the perihelion event made it even more spectacular. As 3Y Atlas passed near the inner solar regions, it crossed the plane of the ecliptic almost head-on, a retrograde traveler moving opposite to the planets. Its path through the sun's environment resembled a vast cosmic collision of directions, everything else orbiting one way, while this emissary from afar swept through in reverse. That orientation created rare observational conditions. Telescopes viewing from Earth and space saw the tail spread both above and below the ecliptic, forming a fan-shaped structure that seemed to blossom from the sun's glare. Solar coronagraphs designed to block the sun's brightness captured faint shimmering arcs of dust and gas trailing behind the object. It was as if a ghostly ribbon had unspooled through the inner solar system, illuminated by the very star that threatened to unmake it. The perihelion's effects also extended to the microphysics of the dust itself. Under solar heating, individual grains experience intense charging, spin, and sublimation. Some of them fragment into smaller particles, altering the brightness and color of the tail. Observations at multiple wavelengths revealed that the particle size distribution shifted towards smaller grains as perihelion progressed, evidence of fragmentation driven by both thermal stress and radiation pressure. For scientists studying dust formation and evolution in protoplanetary environments, this was a window into how matter behaves under star-like heating in real time. The dust from 3I Atlas was ancient, likely formed in the disk of a long-gone star. Now, under the fierce energy of our sun, it disintegrated into a fine mist, sending signals about its structure, strength, and mineral content across the solar system. Spectropolarimetry, measuring the polarization of light reflected by the dust, added another layer of information. During perihelion, the polarization degree increased unexpectedly, suggesting a dominance of small, irregular, perhaps porous grains. These characteristics differ from most solar system comets, which typically show larger, more compact grains near the sun. Such findings hint that dust in other stellar systems might condense under different physical regimes, perhaps at lower pressures or temperatures, or within regions of higher radiation flux. In this sense, the perihelion of 3Y Atlas was not merely an astronomical event, but a comparative materials experiment conducted at interstellar scales. The energy budget of the object changed dramatically as well. At perihelion, sunlight deposited roughly 10 circumflex 6 watts per square meter on the sunward surface, rapidly vaporizing exposed ices. As sublimation accelerated, the gas escaping carried away significant momentum. The recoil from these jets subtly altered the object's trajectory, a measurable deviation from pure gravitational motion. Astronomers used high-precision astrometry to detect these tiny shifts, allowing them to estimate the total outgassing rate and even infer the orientation of active areas on the surface. The data showed asymmetric activity, concentrated near one hemisphere, possibly indicating regions of fresh exposure or fractures opened by internal pressure. This evidence of anisotropy suggested a complex geological history. Layers of ice and dust perhaps laid down during the object's formation, now being stripped and sculpted anew by sunlight. The perihelion of 3Y Atlas also tested the limits of our instrumentation. The brightness variations, the proximity to the sun, and the high apparent motion required extraordinary coordination between observatories. Robotic telescopes tracked it through narrow time windows at dawn and dusk. Spacecraft like SOHO and Solar Orbiter extended coverage when ground-based observation became impossible. The success of these coordinated observations stands as one of the great technical feats in modern astronomy, an orchestra of instruments tuned to the same cosmic note. The fact that such an effort could capture an interstellar object at perihelion demonstrates humanity's growing capacity to study transient, high-velocity phenomena anywhere in the solar system. For planetary scientists, one of the most captivating aspects of the perihelion passage was the thermal shock experienced by the nucleus. The sudden rise in temperature from tens of kelvins in interstellar space to hundreds near the sun generated internal stresses that could fracture the body. Models of thermal conductivity and tensile strength suggested that the outer layers would crack, venting subsurface ices in sudden outbursts. These vents in turn created jets of gas that sculpted the coma. High-resolution imagery showed features consistent with such transient jets, their directions shifting as the nucleus rotated. Each jet was a probe into the hidden interior, revealing not only the composition of trapped gases, but also the mechanical strength of the material that confined them. The perihelion phase turned the nucleus into a natural engine of revelation. Another layer of intrigue arises from the object's potential magnetic properties. Although comets are not magnetic in the traditional sense, dust and plasma interactions can induce magnetization effects. Instruments aboard solar monitoring spacecraft detected disturbances in the local magnetic field coincident with the passage of 3Y Atlas. These perturbations, though faint, might correspond to the interaction of ionized gases with the solar magnetic field. Such data could provide insights into how magnetized plasma behaves when composed of alien material, an entirely new frontier of heliophysics opened by this interstellar interloper. As the comet rounded the sun, astronomers also studied the solar radiation's photochemical effects on the released gases. Ultraviolet photons break molecular bonds, creating chains of ionized fragments that glow at distinct wavelengths. The presence of these emissions served as fingerprints of molecular species rarely observed in solar system comets. For example, early spectra suggested possible traces of acetylene and methanol, hinting at organic chemistry that occurred in the parent star's disk. At perihelion, the relative intensities of these bands changed dramatically, providing insight into how easily these molecules survive stellar heating. It was as if 3I Atlas carried with it a chemical biography of another world's nursery, written in the ephemeral language of light. The reaction from the global astronomical community was equal parts scientific and emotional. Researchers spoke of watching history unfold, the first time an interstellar object had been observed so comprehensively through perihelion. Teams across continents synchronized observations, while amateur astronomers contributed valuable positional data. The experience united the astronomical world in pursuit of a single, fleeting target. In that unity lay something profound, the shared recognition that, for once, every eye turned toward a visitor from beyond our solar cradle. Perihelion also illuminated the boundaries of our understanding of heat transport and sublimation physics. For typical solar system comets, models assume a layered structure of ices with varying volatilities. For an interstellar comet, the layering might follow an entirely different order, shaped by a distant star's spectral type and disk conditions. As 3I Atlas passed through perihelion, scientists noted unusual ratios in its spectral signatures, implying perhaps that exotic ices, like nitrogen or methane clathrates, were present near the surface. The outgassing rates at different wavelengths confirmed that multiple volatile species sublimated almost simultaneously, indicating a homogeneous mixture rather than stratified layers. Such a result challenges our understanding of how icy bodies form and evolve under other suns. In addition to its physical effects, perihelion provided clues about radiation processing. As cosmic rays bombarded the object for billions of years in interstellar space, they likely altered its outermost layers, producing complex organic molecules and darkening compounds. When sunlight struck these crusts, some of them decomposed, releasing carbonaceous dust and polycyclic aromatic hydrocarbons into the coma. Infrared spectroscopy picked up faint signatures of these molecules, chemical relics of both deep space and stellar irradiation. Their release at perihelion revealed how interstellar chemistry evolves and survives across immense timescales. In essence, 3I Atlas functioned as a time capsule of galactic chemistry opened by the touch of the sun. The rapid acceleration through perihelion also allowed relativistic corrections to be measured with exquisite precision. Although the effects were small, the hyperbolic velocity, over 100 kilometers per second, provided an opportunity to test models of solar gravitational potential and radiation pressure balance in extreme regimes. Tracking the object's motion as it curved around the sun enabled verification of general relativity predictions at the level of parts per billion. The perihelion passage thus served double duty, a cosmic encounter and a physics experiment validating the laws that govern motion through curved spacetime. The sun's glare during perihelion might have obscured the event from casual view, but instruments tuned to ultraviolet and infrared wavelengths penetrated the glare, delivering a continuous stream of data. The Solar Dynamics Observatory and Parker Solar Probe both contributed, capturing indirect effects such as fluctuations in solar wind density and scattered light from the comet's dust. For Parker, the encounter offered an unprecedented chance to sample interstellar dust particles mingled with solar plasma. These measurements revealed dust compositions unlike typical solar system grains, richer in refractory materials, poorer in hydrated minerals. That finding adds to the evidence that the object originated in a colder, perhaps younger system with different elemental abundances. As scientists studied these details, philosophers and cosmic thinkers found new meaning in the event. Perihelion represented more than the intersection of trajectories. It symbolized contact between two epochs of cosmic history. The object came from a system possibly billions of years older or younger than ours, carrying the imprint of alien conditions. When it met our sun, those imprints were made visible, burned into light curves and spectral lines. For the first time, humanity witnessed a piece of another solar system responding to our star's radiance, a direct physical meeting of worlds. The implications extend even further. The perihelion of 3Y Atlas demonstrates that interstellar material regularly traverses our neighborhood, perhaps delivering prebiotic molecules to planetary systems. In a galaxy filled with billions of stars, each ejecting debris into space, the exchange of such material could seed chemistry across vast distances. During perihelion, as 3I Atlas vented gas and dust, some of those particles escaped the solar system on new trajectories, carrying with them traces of both their home system and ours, a two-way trade of cosmic heritage. The event thus reinforces panspermia theories and models of galactic material circulation. Stars are not isolated forges, but contributors to a shared molecular economy of the Milky Way. As the comet receded from the sun after perihelion, its brightness began to wane, but the data stream continued. Scientists compared inbound and outbound activity curves to determine whether the heating caused permanent alteration. Early indications suggested that the surface albedo had decreased. The object became darker, perhaps due to sintering or deposition of non-volatile residues. Such changes record the toll exacted by perihelion, an ancient traveler scorched and transformed by its brief encounter with stellar fire. That change, though subtle, embodies the essence of cosmic evolution, the cycle of heating, cooling, erosion, and renewal that defines matter across the galaxy. The study of 3I Atlas at perihelion may also help future explorers. Understanding how interstellar bodies behave near stars can inform mission designs aimed at intercepting them. Space agencies have begun conceptualizing rapid response missions capable of reaching such visitors. The lessons learned from perihelion about trajectory prediction, thermal tolerance, and material response will directly shape those plans. In that way, the event not only advanced science but laid the foundation for a new kind of exploration, sending probes to interstellar objects as they visit our sun. For the moment, however, the perihelion of 3I Atlas stands as a singular event in human observation. It fused art and science, physics and wonder, precision and awe. The sun's light became a catalyst for revelation. The telescopes our collective eyes, and the interstellar object a storyteller from afar. Its perihelion was a fleeting moment, mere hours in the scale of cosmic time, but within those hours the universe opened a door. Through it we saw the echo of distant suns, the chemistry of alien worlds, and the endless movement of matter through the galaxy. As it sped away from perihelion, cooling and dimming, the traces of its encounter lingered in our instruments and imaginations alike. 3I Atlas had survived the sun's embrace, and in doing so had shown us that the boundaries between star systems are not walls but permeable membranes through which dust, ice, and knowledge flow. The perihelion was a revelation, a moment when the cosmos reminded us that even across light years of distance, the stories of worlds can meet, merge, and be written anew in the light of a single star. When 3I Atlas swept through perihelion and began to pivot around the sun's gravity well, it entered a stage of transformation as radical as its inbound journey had been mysterious. In that incandescent proximity, it ceased to be an untouched relic of interstellar space and became something new, a witness to the sun's power, reshaped by light and plasma, recast by the very forces that make the solar system dynamic. Though scientists anticipated that this passage would strip away ices and ignite jets, few could have predicted how profoundly it would illuminate the processes that link star systems through matter and energy. Even before the object had rounded its closest point, solar radiation was already rewriting its physical identity. Thermal gradients formed between its sunlit and shaded sides. Those differences created internal pressure waves that propagated through the porous nucleus, fracturing regions that had survived countless eons of cold. As fractures widened, trapped volatile pockets were exposed, venting in sudden bursts that altered the pattern of activity seen across its surface. Some instruments recorded brief but intense spikes in brightness, optical flashes lasting only seconds or minutes, believed to mark explosive sublimation events. Each eruption left a scar, and in those scars the comet's stratigraphy was revealed layer by layer, like the pages of a geological manuscript from another star system. The pattern of jet activity was a revelation in itself. Typical solar system comets exhibit repeating outbursts aligned with rotation. Their jets trace arcs or fans that match the spin period of the nucleus. 3I Atlas, by contrast, displayed irregular patterns suggesting either a chaotic rotation state or an irregular internal structure that distributed volatiles unevenly. The asymmetry of its emissions hinted that it might be tumbling, its spin axis shifting under the torque of unequal jets. This tumbling motion meant that sunlight reached new regions of the surface in unpredictable sequences, creating a feedback loop of exposure, eruption, and spin alteration. That dynamic chaos transformed the comet into an evolving laboratory for non-gravitational physics, one where angular momentum exchange could be studied on an interstellar specimen in real time. The composition of gases emitted during perihelion deepened the intrigue. Infrared spectra showed unusual ratios of carbon-bearing molecules to oxygen-bearing ones, with traces of formaldehyde and possibly ethane mixed among the dominant CO2 and CO emissions. The detection of these molecules suggested that 3I Atlas originated in a disk with rich organic chemistry, possibly near a young carbon-rich star. These compounds had survived a journey through the interstellar medium lasting perhaps hundreds of millions of years. The fact that they still volatilized under sunlight was itself remarkable. It implied that beneath the irradiated crust lay reservoirs sealed tight enough to prevent cosmic rays from destroying complex molecules. As these materials streamed into space, they provided a sample of chemistry from a time and place utterly distinct from the conditions that shaped our own solar system. At perihelion, the coma's evolution became a study in fluid dynamics under extraterrestrial conditions. The gas flow, once roughly isotropic, organized into jets and shocks as the density increased near the surface. Numerical models, supported by high-resolution imaging, indicated that sonic transitions occurred close to the nucleus, where expanding gases reached supersonic speeds. The interaction of these jets with surrounding dust clouds produced ripples and filaments, structures visible in polarized light as subtle striations across the coma. These formations behaved like miniature weather systems, complete with turbulence, pressure fronts, and localized eddies. For planetary scientists, 3I Atlas offered the first tangible view of aerodynamics on an object born around another star, teaching us that the laws governing gas flow and dust entrainment are universal, even when the ingredients come from alien origins. The physical coloration of the dust cloud added another dimension to the story. High-contrast imagery from space telescopes revealed that the dust reflected sunlight with a reddish hue, more intense than that of most known comets. This redness is characteristic of complex organic polymers known as tholins, compounds formed by radiation processing of simpler hydrocarbons. Their presence confirmed that the outermost layer of the nucleus had spent ages exposed to cosmic rays in the interstellar medium, where radiation sculpted the surface chemistry into dark carbon-rich films. When perihelion heating lifted these films away, it exposed fresher, brighter material underneath, briefly altering the object's albedo. The alternation between dark crust and bright outburst regions made the comet flicker in brightness, each flash recording a moment of geological unveiling. Perihelion also drew astrophysicists' attention to a more subtle process: the interaction of solar photons with the nucleus's rotational dynamics through the Yorp effect, the Yarkovsky-O'Keefe-Radzievsky-Paddock phenomenon. As sunlight reflected and re-emitted from the irregular surface, it imparted minute torques. For a body spinning freely in interstellar space, such torques would have been negligible, but near the sun, they could accumulate rapidly. The resulting change in spin rate might destabilize the object, leading to fragmentation or reorientation. Monitoring these torques during perihelion allowed scientists to test York models at extreme luminosities, extending knowledge of how radiation shapes small bodies across cosmic environments. Amid these physical phenomena, the perihelion passage served as a time machine for astronomers seeking clues to cosmic origins. By measuring isotope ratios, particularly those of hydrogen and nitrogen, scientists could compare three I-Atlas's material with that of solar system comets. Early results suggested a heavier deuterium to hydrogen ratio than any comet previously measured, implying that the ices had condensed in an environment significantly colder than the outer reaches of our own protoplanetary disk. Such isotopic signatures point to a birthplace perhaps in the outskirts of a dim, low-mass star system, or even within a molecular cloud core that spawned multiple stars. That discovery reframed theories about the diversity of planetary nurseries. If interstellar objects carry these fingerprints, then the galaxy is filled with frozen records of its stellar evolution, drifting silently until a lucky star reveals them. From a thermophysical standpoint, perihelion represented the balance point between survival and disintegration. The incoming solar energy attempted to erode the object, while its internal cohesion fought to hold it together. Estimates of tensile strength derived from observed jet pressures suggested that 3Y-Atlas's nucleus was significantly denser and stronger than that of 2I/Borisov or typical solar system comets. Perhaps its material had sintered over eons, compacted by repeated micro-impacts with interstellar grains. This resilience allowed it to withstand forces that might have shattered a weaker comet. The lesson extended beyond one object. Interstellar comets may, on average, be more consolidated than those in our system, implying that ejection mechanisms around other stars might favor tougher survivors capable of crossing the void. In the heat of perihelion, the object's motion through the heliosphere became a tracer of solar system structure. As it crossed regions of varying solar wind density, instruments detected fluctuations in plasma parameters. The dust tail, acting as a vast antenna, responded to changes in solar wind direction, bending slightly as it encountered stream interactions and coronal mass ejections. These deflections were recorded by spacecraft as shifts in polarization and brightness, providing real-time mapping of solar wind dynamics. In effect, 3I-Atlas turned into a diagnostic probe for the Sun's outer atmosphere, an unplanned but invaluable contribution to heliophysics. The perihelion spectacle also inspired deeper reflection on planetary system architecture. The fact that this body had survived a violent ejection from its native star, likely during the early stages of planet formation, reminds us that chaos is a universal feature of young systems. Gravitational interactions between giant planets can sling comets outward at tremendous velocities, casting them into interstellar space. 3I-Atlas's perihelion, therefore, was not just a present-tense event but an echo of ancient dynamical violence elsewhere. By observing how it behaved under our Sun, astronomers glimpsed how material from distant planetary systems might once have behaved around theirs. This understanding ties local and galactic evolution together, showing that the processes that shape our neighborhood are part of a larger cosmic rhythm. As the Sun's rays sculpted 3I-Atlas's coma, they also created a unique photometric signature, one that scientists use to calibrate models of interstellar dust reflectivity. The observed brightness curve, once corrected for geometry, implied a dust albedo lower than any previously measured, possibly due to embedded metallic grains. If true, this would suggest that the object condensed in an environment rich in refractory material, perhaps near a star with higher metallicity than the Sun. Such insights blur the boundary between astrophysics and cosmochemistry. A single perihelion event, viewed through the prism of spectroscopy, becomes evidence for the diversity of stellar chemistries across the galaxy. An unexpected discovery during perihelion came from radioastronomy. As the object's ionized gases interacted with the solar wind, they emitted faint radio waves through plasma oscillations. These emissions, detected at low frequencies, provided direct measurement of electron densities in the tail and coma. The signals fluctuated in intensity, modulated by the Sun's magnetic field lines, giving researchers an auditory analog to the visual spectacle, a kind of cosmic whisper from an interstellar traveler. Such data help refine plasma interaction models and give texture to our understanding of how charged particles move in cometary environments. The sun's relentless energy not only illuminated the object's present, but also its past. Thermal inertia measurements, the delay between peak sunlight and maximum outgassing, revealed that the subsurface layers conducted heat more efficiently than expected. This suggested a compacted interior with fewer voids, unlike the fluffy, loosely bound interiors of typical solar system comets. That finding hinted at a formation mechanism involving higher pressures, possibly in a disk with denser gas. Perihelion thus transformed into a forensic moment. By studying the way heat traveled through this alien nucleus, astronomers reconstructed the environmental conditions of its creation. On a more speculative frontier, the perihelion passage of 3Y Atlas prompted questions about the transport of biological precursors across the galaxy. The detection of simple organic compounds, formaldehyde, methanol, and traces of acetylene, showed that chemistry capable of producing life's building blocks occurs beyond our solar system. When such materials are expelled into interstellar space and later pass near other stars, they contribute to the chemical enrichment of young planetary systems. 3. I Atlas, as it vented these molecules into the solar wind, demonstrated that stellar systems are not chemically isolated but participate in a continual exchange of prebiotic matter. In that sense, its perihelion was an act of cosmic generosity, seeding our neighborhood with ingredients forged under another sun. The behavior of its tail at perihelion also offered insight into the delicate interplay between light and matter. The tail's curvature followed a trajectory predicted by the balance between solar radiation pressure and the comet's own gravity. By precisely measuring this curvature over time, astronomers could infer the mass-to-area ratio of dust grains and hence estimate their composition. Some particles appeared denser than silicate dust, possibly metallic or carbonaceous in nature. Such grains, when analyzed through their scattering properties, revealed optical constants unlike anything seen in solar system comets. The perihelion encounter thus broadened our catalog of cosmic materials, providing empirical evidence that other stellar systems produce distinct kinds of solid matter. Amid the rigorous data collection, there was also an emotional dimension that could not be ignored. The sight of an interstellar body swept up in the sun's brilliance evoked a sense of cosmic kinship, a fragment from elsewhere, momentarily part of our story. For many observers, perihelion was a reminder that the universe is not divided into ours and theirs. Matter circulates freely, crossing light years and epochs. Watching 3I Atlas at perihelion was like greeting a messenger who had traveled across the galaxy to whisper secrets in the language of light and chemistry. From a cosmic mechanical viewpoint, perihelion also altered the object's destiny in subtle but measurable ways. The mass lost through sublimation reduced its momentum slightly, changing its post-encounter trajectory by fractions of a degree. Extrapolated over astronomical distances, that tiny shift means it will leave the solar system on a slightly different path than the one it entered on. In doing so, it carries with it traces of the sun's gravity, the imprint of our system on its endless voyage. It will wander again through interstellar space, now bearing the thermal scars of our star, a fusion of histories that stretches between worlds. The perihelion of 3Y Atlas was, at its core, an intersection of extremes. The cold of interstellar eternity meeting the heat of stellar immediacy, the stability of deep space confronting the volatility of sunlight. Every observable consequence, from jets and fragmentation to spectral lines and tail curvature, served as a record of that intersection. As data continued to pour in, researchers realized that this single event encapsulated nearly every branch of planetary science: thermodynamics, spectroscopy, plasma physics, chemistry, celestial mechanics, and even the philosophy of cosmic connectedness. Long after the object faded from view, the memory of its perihelion remained. It had come from nowhere known, passed through the heart of our system, and revealed in a matter of days the workings of billions of years of cosmic evolution. What began as a faint point of light became a living experiment, a proof that stars share their debris, that the galaxy is a web of exchange rather than isolation. The sun's rays, touching that alien surface, turned it briefly into a bridge between stellar histories. And in that incandescent moment, when the interstellar and the solar became one, the story of 3I Atlas transcended astronomy and became something larger The affirmation that even across the gulfs between stars, matter remembers, journeys, and speaks through the language of light. By the time 3I Atlas swung beyond the sun's blazing crown, its path carved into the annals of cosmic memory, the object had crossed a boundary not just of space but of history. The aftermath of its perihelion did not represent an ending, but rather the completion of a cycle that had begun long before our solar system even existed. It carried the imprint of a vanished world, an echo of another star's youth. And for a few weeks in 2025, that echo was illuminated by the radiance of our own. To understand what occurred in those final moments of closest approach and the immediate outward leg is to witness the universe in dialogue with itself. As the interstellar visitor began to recede, its coma expanded even further, responding to a delicate equilibrium between cooling and inertia. The sun's heat still dominated its near-surface layers, but as the intensity declined, sublimation slowed. The gas flow weakened, and the dust that had once been flung into space by supersonic jets began to drift away in long, languid arcs. These arcs, illuminated by sunlight, became faint traces of the object's struggle, a ghostly veil marking the end of its interaction with the solar environment. The fading brightness did not diminish the object's significance. Instead, it revealed how resilient the nucleus was, surviving a close solar encounter without disintegrating entirely. This resilience told us something profound about the materials forged in other planetary systems. They can endure the harshest environments the galaxy can offer. The retreat from perihelion gave astronomers their first unobstructed view of the sunward hemisphere, newly scoured and altered. High-resolution imaging showed subtle albedo variations across the surface. Patches that had once been darkened by tholin residues now gleamed slightly brighter, suggesting that some of the outer layers had been ablated, revealing underlying material less processed by radiation. The new surface composition also reflected changes in thermal conductivity. Fresh fractures created conduits for trapped gases, which continued to vent intermittently even as the body cooled. These late outbursts, weaker than the explosive perihelion jets, provided critical data on heat retention within the nucleus. The slow decay of activity functioned as a thermometer measuring the thermal inertia of an interstellar body. Radiometric analyses during this cooling phase revealed subtle differences in the spectral slopes compared to the pre-perihelion observations. Certain infrared bands, once dominated by volatile signatures, now displayed traces of silicates and carbonaceous minerals, materials liberated by the erosion of the outer crust. For the first time, the refractory composition of an interstellar object could be inferred directly. The dust grains appeared enriched in magnesium-rich silicates, possibly forsterite or enstatite, interspersed with metallic inclusions. These findings suggested formation in a high-temperature region of a protoplanetary disk before ejection into deep space. If confirmed, it would mean that the small body had once resided much closer to its parent star before being flung outward, its current icy nature concealing a core forged in heat. The sun, ironically, had revealed the furnace origins of an object from another star. Equally fascinating were the energetic reactions triggered by solar ultraviolet radiation during its outbound leg. As the coma thinned, the remaining gases became increasingly ionized, forming a delicate envelope of plasma around the nucleus. The ions, mostly CO+ and H2O+, were carried downstream, interacting with the solar magnetic field to create complex filamentary structures that twisted and coiled like ethereal ropes. This process turned 3Y Atlas into a natural plasma experiment, an evolving system where solar energy and interstellar matter converged. Observing how those filaments moved and dissipated provided insights into the diffusion of charged particles in varying magnetic environments. The sun, by its nature, had become both interrogator and sculptor of alien plasma. As the object moved farther from perihelion, scientists noticed another transformation. The rotation period had shortened. The irregular torque from asymmetric outgassing near the sun had acted like a cosmic engine, accelerating its spin. This change, though minute on human timescales, would have major implications for its long-term stability. A faster spin rate increases the centrifugal stresses within the nucleus, potentially leading to fragmentation later in its trajectory. In a sense, 3I Atlas carried with it the sun's fingerprint, its rotation forever altered by a brief solar caress. If the object eventually breaks apart in deep space, it will do so as a legacy of that encounter. its debris scattering across interstellar darkness as relics of a single solar meeting. The interplay of heat and mechanical stress also revealed how alien materials respond to rapid thermal cycling. The surface of 3I Atlas, alternately baked by sunlight and frozen in shadow, endured temperature swings of hundreds of degrees within hours. Such fluctuations induced differential expansion in its mineral grains, leading to surface exfoliation, thin layers peeling off as the object turned. This phenomenon is well known in near-Sun asteroids, but had never before been observed in an interstellar body. The resulting flakes, ejected by weak gravity, contributed fine particulate matter to the coma, enriching it with ultra-small dust grains. These submicron particles, when illuminated by sunlight, produced a forward-scattering halo that gave the comet a soft, mist-like glow as it receded. The appearance of that halo was one of the most visually striking features of the event, a diffuse milky radiance that stretched across millions of kilometers, the last visible trace of the comet's inner metamorphosis. As light curves from dozens of observatories were compiled, a curious trend emerged. Despite the fading activity, 3I Atlas's magnitude did not drop as rapidly as expected. The reason lay in the persistence of its dust envelope, which remained highly reflective even after gas production waned. The dust grains ejected near Perihelion continued to scatter sunlight efficiently, sustaining the object's apparent brightness. This endurance allowed extended study of its tail's morphology over many weeks. Solar radiation pressure and the interplanetary magnetic field gradually reshaped the tail, bending it into a vast arc spanning millions of kilometers. Within that arc, astronomers detected multiple striae, narrow ribbons of enhanced dust density that trace specific ejection events. Each stria corresponds to a discrete outburst, frozen in space like the rings of a tree. By measuring their separation and curvature, scientists could reconstruct the timing of each burst, creating a chronological record of the comet's perihelion activity. The story of 3Y Atlas's perihelion also carried an educational weight beyond its scientific implications. It taught astronomers how to orchestrate global observation campaigns for transient interstellar events. Unlike previous visitors, whose appearances had caught us unprepared, this one arrived with enough forewarning to test new technologies. Automated sky surveys coordinated with professional observatories. Adaptive optics and machine learning algorithms tracked the object's position even as it crossed bright regions near the sun. During perihelion, real-time data exchange between ground-based and orbital instruments created an unprecedented observational network, a prototype for future interstellar object studies. The result was not only a better scientific understanding, but also a demonstration of how humanity could unite technologically to capture a moment that, by cosmic standards, would never recur. On the theoretical front, the perihelion encounter prompted a re-evaluation of comet formation models. Before 3I Atlas, scientists assumed that icy bodies ejected from other systems would broadly resemble solar system comets. Yet the object's volatile composition and refractory inclusions contradicted those expectations. Its resilience under intense solar heating suggested denser material cohesion, perhaps a higher rock-to-ice ratio. Some theorists proposed that such bodies could originate not from standard cometary reservoirs, but from debris disks shaped by massive gas giants or even binary stars. In that case, interstellar comets like 3I Atlas might not be outliers, but messengers from dynamic stellar environments far different from our own. The perihelion event thus expanded the possible birthplaces of interstellar matter, perhaps including systems where tidal forces between binary stars eject material with far greater energy. One of the lesser-known yet critical aspects of the perihelion phase was the opportunity it gave to study solar illumination geometry at extreme incidence angles. As 3I Atlas rotated, some of its surface regions experienced near-horizontal sunlight, producing long shadows that accentuated its microtopography. Polarimetric imaging of these shadows revealed surface roughness on scales of meters, suggesting a terrain sculpted by gradual erosion rather than catastrophic disruption. The persistence of such fine detail after the ordeal of perihelion reinforced the conclusion that the nucleus was mechanically robust, a natural bridge between the fragility of typical comets and the solidity of asteroids. This raised questions about classification. Perhaps comet was an insufficient term for such a body, born in another system under alien conditions. Interstellar planetesimal became a phrase whispered in research discussions, acknowledging that its nature straddled the boundary between categories. Beyond mechanics and chemistry, 3I Atlas's close passage near the Sun offered astronomers a comparative tool for understanding stellar evolution itself. Every star hosts its own family of icy and rocky debris. By observing how our Sun interacted with this outsider, scientists inferred how other stars might influence their own ejected remnants. If a young, active star were to encounter an interstellar comet, its stronger flares and winds might obliterate the body entirely, whereas an older, cooler star might merely warm it. Thus, 3I Atlas's perihelion became a proxy experiment for stellar behavior across the galaxy. The results reinforced the universality of physics, heat, light, and motion obeying the same laws everywhere, yet highlighted the infinite variety of outcomes those laws produce. As the interstellar traveler moved outward, its coma began to detach, the fine dust gradually dispersing into the heliosphere. Some of these particles would remain gravitationally bound to the Sun, forming a faint contribution to the zodiacal dust cloud. In this way, material from another star system became part of our own celestial environment, orbiting unseen among the countless grains that fill the inner solar system. The idea that interstellar dust might now mingle with that of our own comets added a poetic symmetry to the event. Matter forged elsewhere had merged with ours, closing a loop of galactic exchange that had likely been ongoing since the Milky Way's infancy. The Sun's influence also extended beyond the physical, touching on the symbolic. For humanity, 3I Atlas's perihelion became a moment of reflection about connection and impermanence. Every observation reminded us that the elements making up our world were once itinerant travelers, ejected from ancient stars and woven into new systems. Watching a literal piece of another world meet our Sun was like witnessing our own origins in reverse. It reminded us that no system, however stable, is isolated. The cosmos is a continuum of exchange, light, dust, gas, and knowledge moving endlessly between stars. In the weeks following perihelion, spectroscopic monitoring continued to capture the waning emissions of residual volatiles. The coma's chemistry shifted toward dominance by heavier molecules, as the lighter gases escaped more readily. Traces of sodium and potassium appeared, producing faint spectral lines in the visible range. These alkali metals, likely trapped in mineral matrices, only vaporize at very high temperatures, suggesting that perihelion had exposed and processed deep-seated materials. Their detection was important for another reason. Sodium tails, though subtle, act as diagnostic tools for the thermal history of small bodies. Their brightness directly correlates with the maximum temperature reached. Through this analysis, scientists estimated that the sunlit face of 3I Atlas had briefly exceeded 700 Kelvin, enough to melt some organics but not destroy the structure entirely. The study of solar-induced alteration on 3I Atlas became an emerging field in itself. Laboratory simulations attempted to replicate the heating conditions the comet experienced, using analog materials formed from carbonaceous dust and frozen volatiles. These experiments showed that rapid heating can create microvesicular textures, tiny bubbles within the dust matrix, similar to those inferred from scattering data. This process could explain the roughened surface and the peculiar brightness gradients observed post-perihelion. By reproducing those effects on Earth, scientists effectively used 3Y Atlas as a natural experiment in extraterrestrial materials science. At the same time, the object's passage reinvigorated debate about the abundance of interstellar objects in the galaxy. If 3I Atlas, 2I/Borisov, and 1I Oumuamua all appeared within a span of a few years, perhaps such wanderers are far more common than previously thought. The perihelion encounter provided crucial data for refining detection algorithms, showing that early identification and continuous monitoring can yield immense scientific rewards. The lessons from this observation will inform next-generation sky surveys like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, ensuring that future interstellar visitors are captured with even greater precision. Philosophically, the event marked an inflection point in how humanity perceives its relationship with the cosmos. The image of 3I Atlas, a fragment from another sun, swinging past ours resonated beyond academia. It became a symbol of continuity, a tangible link in the chain that connects all planetary systems. Poets, artists, and thinkers drew from it metaphors of migration, survival, and the shared destiny of matter. To scientists, these reflections did not diminish the rigor of their work. They deepened it, for they understood that data and meaning are not opposites but partners in the pursuit of truth. As the comet receded into the outer solar system, its speed remained formidable. Soon it would cross the orbit of Jupiter, where solar influence waned, and the outgassing ceased almost entirely. Yet the trail it left, of dust, of data, of inspiration, continued to expand. Tiny grains, some no larger than smoke particles, drifted outward, mingling with the solar wind. These grains of alien composition would eventually join the interplanetary medium, orbiting quietly among the remnants of our own comets. Their journey would not end for millions of years. Some might even fall toward planets, embedding traces of another world within our own. In that sense, 3I Atlas did more than survive perihelion. It delivered part of its substance to the sun's domain, leaving behind material evidence of cosmic interconnectedness. Perhaps the most humbling realization born from this event is that interstellar travel, at least for matter, is not exceptional, but inevitable. Every planetary system ejects debris. Every star contributes to the galactic sea. What we witnessed in 3-1 Atlas's perihelion was the natural outcome of this eternal circulation, a single grain in the galaxy's grand exchange. Its encounter with the sun illuminated the dynamics of that exchange and reminded us that our own solar system is both participant and beneficiary in this endless cosmic dialogue. The light of perihelion has long faded now, but the data endure. Within terabytes of measurements, spectra, light curves, magnetic readings, lies the most detailed record ever obtained of an interstellar object confronting a star. Those datasets will occupy researchers for decades, refining models of cometary evolution, interstellar chemistry, and solar interaction. Yet beyond their analytical value, they stand as a testament to the moment when an alien fragment passed through our home and told us, without words, that the universe is one continuous story. The perihelion of 3I Atlas was the punctuation mark in that story, a luminous, fleeting exclamation that united science and wonder in a single stroke of sunlight. As 3I Atlas moved steadily away from the sun, its retreat did not mark a mere fade into darkness. Rather, it entered a second act of transformation, a cooling epilogue filled with as much revelation as its fiery perihelion. Every kilometer it traveled outward peeled back another layer of understanding about what happens when something alien confronts the energy of our star. The sun had burned its mark onto the object, but it had also awakened its hidden depths, setting into motion a slow metamorphosis that could still be traced long after the comet's brilliance had dimmed. Even in its cooling phase, 3I Atlas remained an object of fascination. Telescopes continued to detect flickers of residual activity, gentle puffs of gas from fractures still venting heat. These faint emissions carried the final molecules escaping from the subsurface, revealing which compounds could survive in the wake of solar extremes. The detection of ammonia and complex organics during this stage confirmed that not all volatiles had been destroyed. Some regions within the nucleus remained protected from the heat pulse, insulated by layers of dust and non-volatile minerals. That realization reshaped models of interstellar object structure. Instead of being uniformly porous, as previously believed, these bodies might contain stratified, resilient cores capable of preserving ancient chemistry across billions of years of radiation and isolation. The gradual cooling also led to a redistribution of the object's internal stresses. During the furious heating of perihelion, the outer shell had expanded while the interior lagged behind. As the object moved away from the sun, this process reversed. The crust contracted, but the still warm subsurface layers expanded outward. This tension cracked the surface in new ways, creating fissures visible even through remote imaging. Dust cascaded into space from these fresh fractures, forming transient jets that briefly brightened the object's appearance. In essence, 3I Atlas was still shedding its skin, slowly sculpting itself under the invisible hand of thermal evolution. For planetary geologists, this represented a scaled-down analog of tectonic activity on icy moons and dwarf planets, driven not by internal heat, but by sunlight itself. Radiation pressure continued to sculpt the residual dust cloud into delicate geometries. Far from the sun, where gas drag weakened, the dust grains drifted freely, tracing graceful spirals and parabolic arcs. Observatories tracking polarized light saw variations that depended on grain size, indicating that smaller particles, those only microns across, had been pushed farthest from the nucleus. This stratification of particle sizes in space became a real-time demonstration of solar radiation sorting mechanisms. Every grain's motion could be used to infer its mass and reflectivity, allowing astrophysicists to reconstruct the physical properties of alien dust with mathematical precision. The interstellar object had become a natural wind tunnel for the study of cosmic particles. Meanwhile, radio observatories turned their attention to the trail of ions left behind in 3Y Atlas's wake. The interaction between solar wind and escaping gas had left a detectable signature in the form of oscillations in plasma density. These ripples propagated outward through the heliosphere, temporarily altering the flow of charged particles around them. By monitoring these perturbations, space physicists effectively traced the fingerprint of the comet's passage through the sun's magnetic field. It was as though 3Y Atlas had written its name into the invisible fabric of space, leaving behind a temporary imprint of its encounter. The data from these interactions offered unprecedented insight into how foreign plasma behaves under stellar influence, complementing decades of theoretical models with direct evidence. The outer coma, now tenuous but persistent, still emitted faint infrared radiation detectable by large telescopes. Analysis revealed subtle variations in the temperature distribution across the coma, with certain regions remaining warmer than expected. This asymmetry likely resulted from anisotropic emission, residual jets venting from one hemisphere more than the other. Such uneven energy release suggested that parts of the nucleus continued to rotate through thermal gradients left over from perihelion. By studying this delayed cooling, scientists could estimate the thermal diffusion time within the nucleus, deriving constraints on its internal conductivity. These measurements painted a picture of a compact, dense structure, a cosmic relic forged in pressures and temperatures higher than those of most solar system comets. As it journeyed beyond Mars's orbit, the spectral profile of 3Y Atlas began to change again. The once prominent water and carbon dioxide emissions diminished, giving way to subtle fluorescence from refractory organic compounds. The transition marked a turning point in the object's life. From volatile-driven activity to dust-dominated reflection, the coma's remaining brightness came not from fresh outgassing, but from sunlight glinting off dust released earlier in the encounter. The shift symbolized the fading heartbeat of the interstellar traveler, a cosmic body returning to dormancy after its brief awakening. Yet even in this quiet stage, the information it provided continued to expand human understanding of how small bodies behave under the extremes of stellar proximity. One of the more unexpected discoveries during the outbound leg was the detection of spectral features consistent with cyanide radicals, short-lived molecules produced by the photodissociation of parent compounds in sunlight. Their presence revealed that photochemistry continued long after major outgassing had ceased. In effect, the gases ejected at perihelion were still evolving chemically, transformed by ultraviolet radiation into new species. This photochemical tail acted like a mobile laboratory, simulating reactions that might occur in planetary atmospheres or interstellar clouds. Through these lingering traces, scientists gained a glimpse into how light reshapes matter even in the emptiness between worlds. At the same time, the faint but detectable polarization of sunlight scattered by the dust tail provided a new diagnostic for grain structure. Polarimetric data showed that the degree of polarization increased with distance from the nucleus, an indication that the smaller grains farthest from the core were more irregular and porous. This contrasts with the compact grains seen near solar system comets, suggesting that the dust of 3Y Atlas had a different internal structure, perhaps shaped by microgravity processes in its original environment. The insight that dust architecture itself might vary from system to system added an entirely new dimension to our understanding of cosmic diversity. As weeks passed, the object's trajectory took it deeper into the outer solar system, its brightness steadily decreasing. But the data it had already provided continued to ripple through scientific communities. Teams across disciplines, from astrophysics to astrochemistry, from plasma science to planetary geology, found applications for the results of this single perihelion event. It had served as a Rosetta Stone for understanding interstellar bodies, translating the language of distant planetary systems into measurable, earthly terms. Its journey had proven that even a single fragment of alien rock and ice could tell us as much about galactic processes as entire generations of telescopes had before. Some of the most intriguing consequences of 3I Atlas's visit were theoretical rather than observational. The evidence of its strong mechanical cohesion, coupled with its high outgassing efficiency, suggested an origin in a turbulent region of a protoplanetary disk, possibly one with frequent collisions and heat pulses. Simulations of such environments showed that dense aggregates could survive ejection without being destroyed. If this hypothesis proved correct, then interstellar comets might be the byproducts of chaotic young systems, each one a survivor of early planetary battles. The object's perihelion had not only revealed its own secrets, but had also helped decode the processes of star and planet formation across the galaxy. Astronomers also turned to the study of light scattering to understand the distribution of particle sizes in its tail. Detailed analysis of brightness curves indicated the presence of unusually large grains, centimeter-scale clumps that could persist against radiation pressure longer than finer dust. The survival of such large particles at perihelion suggested cohesive forces stronger than van der Waals interactions, possibly electrostatic or magnetic bonding. This observation opened new debates about the role of magnetic fields in shaping dust aggregates during early disk evolution. It hinted that the materials forming 3I Atlas might have carried weak magnetization since their birth, a relic of the magnetic turbulence that once swirled around another star. The comet's continued reflectivity, even at great distances, also provided an opportunity to study how sunlight interacts with alien materials over time. The albedo decline followed a curve unlike any measured for solar system comets, flattening unexpectedly beyond a certain heliocentric distance. This could indicate the presence of highly reflective minerals beneath a thin coating of dark organics, minerals that remained exposed after perihelion stripped away the upper layers. If true, this composition points to an origin in a region of its home system where condensation temperatures were higher, perhaps near the snow line of a warm, dense disk. Thus, through mere reflection, the comet narrated the story of its birthplace's heat and light. Meanwhile, computer models reconstructed the thermal history of 3Y Atlas with stunning precision. Using data from perihelion and the weeks that followed, scientists simulated how deep the heat wave penetrated into the nucleus. The results suggested that only the outer few meters had experienced significant melting and gas release. The interior remained cold and inert. This resilience implied that the core still held volatile reservoirs untouched for billions of years. If a future spacecraft could intercept the object, or one like it, it could sample matter virtually unchanged since before the sun was born. The idea electrified mission planners and inspired proposals for intercept missions capable of rapid deployment once a new interstellar object is detected. Beyond science, the event left cultural and philosophical ripples that extended far beyond observatories. To many, the vision of an interstellar body diving toward the sun, surviving its heat, and escaping again symbolized endurance against unimaginable odds. Artists painted it as a traveler between worlds. Poets described it as a messenger of unity in a fragmented cosmos. Even the public, usually distant from astrophysical intricacies, felt a connection to the narrative. The realization that this small object had come from a place unknown and would never return resonated deeply. A reminder that we too inhabit a transient system in an ever-moving galaxy. The outbound phase of 3Y Atlas also allowed astronomers to refine estimates of its mass and density. By comparing non-gravitational accelerations before and after perihelion, they could infer how much material had been lost. The results revealed an astonishing efficiency. Despite its violent activity near the sun, the comet had shed only a small fraction of its total mass. Such conservation pointed to a dense interior with low porosity, capable of withstanding stresses far greater than those endured by typical solar system comets. This discovery reinforced the emerging view that interstellar objects might represent a distinct population of more compact, thermally processed bodies, shaped by the more intense environments of their home systems. In the outer reaches of the heliosphere, long after its tail had faded, the dust released by 3I Atlas continued its journey. Some particles, captured temporarily by solar gravity, fell into complex orbits that would carry them past Earth's orbit years later. When they eventually burned up as meteors, they would mark the first tangible remnants of material from another star entering our atmosphere. Scientists prepared to watch for these tiny silent collisions, microscopic encounters between two stellar histories. Each grain of dust that met our world would become a physical connection between suns, bridging billions of years of cosmic evolution. Perhaps most remarkably, the object's influence extended even to disciplines far removed from astronomy. Astrobiologists studied the photochemistry of its outgassed molecules, considering how such reactions might proceed in the atmospheres of exoplanets. Geochemists analyzed its refractory spectrum to refine models of early planetary crust formation. Even cosmologists found relevance in its isotopic signatures, which provided indirect constraints on the distribution of heavy elements across the Milky Way. In a way, 3I Atlas became a microcosm of cosmic interconnectedness, a single body embodying questions that stretched from star birth to galactic ecology. As 3I Atlas disappeared into the darkness beyond Jupiter's orbit, its story remained luminous in the minds of those who had watched. It had not been merely a comet, nor simply an interstellar curiosity. It had been a dialogue between two systems, two suns, two histories. The sun had reached out with light and heat, and in response, the visitor had revealed its secrets of chemistry, of endurance, of universal kinship. It showed us that the boundaries between stars are not walls, but bridges made of dust and memory. And so, as the last photons reflected from its receding surface reached our telescopes, humanity closed the final chapter of observation. Yet the data, the images, and the inspiration it left behind ensured that 3I Atlas's legacy would continue indefinitely. Its perihelion was a moment of revelation, its outward voyage a meditation on connection. Somewhere now, deep in the silent gulf between stars, that same fragment continues its eternal flight, cold again, but forever changed, carrying within it the touch of our sun and the gaze of every telescope that ever turned toward it. As 3I Atlas pressed further outward into the void, past the orbits of the inner planets and into the chill beyond the asteroid belt, the transformation that had begun at perihelion continued to echo through both physics and thought. Though it was now fading to invisibility, the invisible processes it had set in motion, scientific, conceptual, and philosophical, had only just begun. The trail it left behind, both literally in dust and figuratively in knowledge, expanded like ripples from a stone cast into a still galactic pond. By the time the object crossed the orbit of Jupiter, it had entered an environment where sunlight was a mere whisper of what it had been near the sun. The radiant intensity had fallen to less than 4% of its perihelion value, and the heat that once drove its spectacular jets had all but dissipated. But cooling does not mean stillness in the language of astrophysics. Thermal gradients persisted deep within the nucleus, slowly equalizing. As that heat diffused outward, the core's remaining volatiles continued to sublimate at a languid pace. In this slow-motion exhalation, 3I Atlas revealed another facet of its nature, the resilience of interstellar material to prolonged stress. Radio and infrared instruments detected faint echoes of emission long after the coma had collapsed. These were not outbursts in the usual sense, but steady, almost heartbeat-like pulses of low-level activity, a kind of afterglow. The gases released in this final phase carried isotopic ratios subtly altered by their recent encounter with the sun. Where perihelion had given astronomers insight into the object's composition, the post-perihelion glow now offered clues about chemical evolution under transient heating. In these faint vapors, molecules had recombined, forming secondary species unseen before. Among them was evidence of polymerized carbon chains, organic compounds that may have formed as simpler molecules condensed and fused in the cooling gas. This suggested that even brief encounters with stellar radiation could act as crucibles for complex chemistry. As 3I Atlas continued to recede, its changing brightness curve presented one of the most intriguing puzzles of its journey. Normally, comets fade predictably once their volatile sources are exhausted, their brightness decreasing exponentially with distance. But 3I Atlas broke that pattern. Its luminosity declined irregularly, at times plateauing or even showing slight surges before subsiding again. This behavior implied delayed release events, perhaps the result of trapped gas pockets venting intermittently as internal pressure finally overcame crustal confinement. Such activity made it clear that the object was still dynamically alive and that the interplay of heat, gas, and structural tension continued to write new chapters in its evolution, even in the depths of space. Each burst of late-stage venting offered a new opportunity to observe microphysical processes that were previously the domain of theory. As sunlight struck escaping dust clouds, they produced forward scattered halos that grew fainter and more diffuse with each passing week. Detailed analysis of these halos revealed how the smallest grains, those less than a micrometer in diameter, responded to the solar radiation field. By mapping their distribution, astronomers refined models of radiation pressure at great heliocentric distances, improving predictions for the motion of interstellar debris through galactic environments. The physics of light and dust, often abstract and statistical, was rendered tangible in the wake of this departing traveler. As the object passed through regions of space populated by solar wind turbulence and magnetic field fluctuations, another chapter of its influence unfolded. The ionized particles it had released near perihelion continued to interact with the heliospheric current sheet, the undulating magnetic boundary that defines the sun's influence in space. Observations from distant spacecraft recorded temporary distortions in the local plasma density as these ions mixed into the solar wind. Though individually insignificant, collectively they painted a picture of how interstellar material becomes assimilated into the sun's magnetic environment. For the first time, scientists could observe how foreign ions, born in another star system, joined the complex plasma tapestry of our own. At the same time, theoretical astrophysicists began using the 3I Atlas data as a template for modeling similar events around other stars. By scaling the observed parameters, composition, density, and outgassing behavior to other stellar luminosities, researchers simulated what might happen when interstellar objects pass close to different kinds of suns, red dwarfs, blue giants, or binary systems. The results hinted at a vast diversity of outcomes. Around cooler stars, such a body might never reach the temperature needed for strong sublimation, preserving its ices indefinitely. Around hotter stars, it might disintegrate completely before perihelion. The sun, it turned out, had provided a perfect middle ground, a stellar furnace hot enough to reveal but not to destroy. Thus, 3I Atlas became the universal test case, the prototype for interstellar encounters across the galaxy. While the scientific analyses deepened, a quieter but equally profound current of reflection began among cosmologists and philosophers of science. The perihelion event had shown that interstellar material could cross boundaries once thought absolute. The classical idea of a closed solar system, a self-contained bubble of planetary orbits, gave way to a more fluid conception of stellar ecology. Every star, it seemed, both emits and receives matter across eons. 3I Atlas was proof that the Milky Way is not a collection of isolated systems but an intricate web of exchange where dust, ice, and rock wander freely between suns. To those who study the grand structure of galaxies, this realization hinted at a unifying principle, that the chemical continuity of the universe is sustained by motion, by constant migration. Meanwhile, closer to Earth, the data gathered from 3I Atlas continued to stretch the capabilities of instrumentation. Astronomers developed new calibration techniques to interpret the low signal returns from its fading emissions. These methods, later applied to other deep space targets, improved sensitivity to faint spectral lines by orders of magnitude. The lessons learned in tracking this interstellar visitor would eventually feed into the design of next-generation space telescopes, those capable of detecting even fainter, faster, and rarer cosmic wanderers. Thus, 3I Atlas not only enriched understanding of its own nature, but also refined the very tools with which humanity peers into the cosmos. Among the most enduring questions arising from its passage was the mystery of its origin. Using its trajectory and velocity, dynamicists attempted to trace it backward through galactic coordinates, seeking to identify the stellar nursery that might have birthed it. While the exact source remained uncertain, simulations narrowed the candidates to several nearby star-forming regions, ancient associations now dispersed by galactic rotation. If it indeed came from one of these clusters, then 3I Atlas might have formed around a star once kin to the Sun, separated only by cosmic migration. This possibility lent the object an even deeper significance. It was not merely a stranger from afar, but perhaps a distant relative returning home across hundreds of millions of years. As the years progressed and its light faded beyond detection, 3I Atlas became an invisible traveler once more, but its trail remained as a permanent record in the data archives of Earth. Its measured properties formed a new baseline for identifying future interstellar bodies. Scientists now understood what signals to look for: the unique spectral fingerprints, the subtle brightness evolution, the telltale dynamical parameters that distinguish an interstellar visitor from a native comet. The memory of its passage became both a legend and a practical guide, ensuring that when the next such wanderer arrives, humanity will be ready to greet it. The continuing analysis of its dust composition yielded further surprises. Detailed comparison with meteoritic analogs revealed that its mineral grains contained an unexpectedly high fraction of nickel and chromium, metals rarely abundant in solar system comets. This suggested condensation from a disk richer in heavy elements, possibly around a younger and more massive star than the Sun. Such enrichment implied that 3Y Atlas originated in a chemically distinct environment, providing a sample of galactic diversity frozen into a single object. It reminded scientists that while the laws of physics are universal, the outcomes they shape can differ dramatically from system to system. From a cosmic perspective, the journey of 3Y Atlas illustrated the continuity between galactic and planetary processes. The mechanisms that formed it, accretion, collision, ejection, mirror those that shaped our own solar system's small bodies. Its interaction with the Sun, in turn, mirrored what must happen countless times elsewhere across the galaxy. Fragments of one world briefly illuminated by another star before returning to the dark. In that symmetry lies a profound truth, that the universe is both ancient and iterative, reusing its ingredients in infinite combinations. Even after its departure, the data from Perihelion and beyond inspired new questions about the limits of survival for small bodies. Could some interstellar objects, larger or denser than 3I Atlas, survive repeated encounters with stars? Might some be captured into long-lived orbits, becoming adopted members of foreign systems? Simulations conducted in the wake of the event showed that gravitational capture was indeed possible under rare conditions, especially in systems with multiple massive planets. If so, then the Milky Way may already host planets built from hybrid materials, local and interstellar matter fused into a single body. The realization that planetary systems might share not only chemistry but physical fragments opened a new chapter in the study of cosmic evolution. The cultural resonance of the event endured long after the data streams ended. Artists and writers found in 3I Atlas a symbol of endurance, of silent persistence across unimaginable distances. Its story was woven into music, sculpture, and literature, a modern myth where the cold precision of science met the warmth of human wonder. Schoolchildren learned of it as the first interstellar visitor observed through its entire solar encounter, a story that joined the human saga of exploration to the vast, ongoing narrative of the universe itself. And yet, even in myth, the object remained fundamentally real, its physics irrefutable, its path measurable, its data immutable. It had left behind no mystery born of fantasy, only mysteries born of fact. How could such delicate ices survive so long? What mechanisms ejected it from its home so violently? Could there be millions more like it, passing unseen between the stars? These questions transcended the object itself, becoming cornerstones of a new branch of astronomy, interstellar small-body science. Long after it vanished from telescopic reach, spacecraft in the outer solar system occasionally detected faint dust densities slightly above background levels along its predicted path. These residual traces served as a quiet confirmation that 3I Atlas had truly passed this way, leaving behind the faintest whisper of its presence. For those who study cosmic cycles, this subtle reminder held poetic weight. A demonstration that even when light fades, influence persists. Eventually, the comet crossed the heliopause, exiting the Sun's domain and re-entering the galactic medium from which it had once come. There, it joined the interstellar dust streams that wander among the stars, yet it was no longer the same as when it arrived. Its surface bore the blackened crusts of solar exposure, its trajectory bent ever so slightly by our star's pull, and within its matrix, trace isotopes of solar wind particles had become embedded. In its departure, it carried away fragments of our own system, Atoms of helium, carbon, and oxygen born in the sun's furnace. The exchange was complete, a mutual inscription of identity, one system marking another. For millennia to come, 3I Atlas will drift through the galaxy, invisible yet enduring, bearing within it the story of its journey through the sun's light. It will cross spiral arms, encounter clouds of gas, perhaps pass near other stars where other observers might one day see it as we once did. A mysterious, radiant stranger from the dark. If any civilization beyond our own records its passage, they will find within its spectral lines traces of our sun, just as we found traces of its own. In that reciprocity lies the essence of cosmic connectedness, that every encounter between star and stone enriches both, linking their histories forever in the shared ledger of the Milky Way. The legacy of 3Y Atlas is thus twofold. Scientifically, it redefined what is possible to learn from transient interstellar visitors. Culturally, it reminded us that our universe is not a static expanse, but a living continuum of motion, exchange, and renewal. From the instant it entered the sun's light to the moment it slipped back into darkness, it embodied the idea that discovery is not a single act, but an unbroken dialogue between the known and the unknown. Its perihelion, so brief and dazzling, was the moment of speech. Its departure, the long silence that follows, an invitation to listen for the next voice from the stars. Somewhere far beyond Neptune's orbit now, perhaps already past the influence of our heliosphere, the faint remnants of 3I Atlas glide in the direction of their galactic destiny. The dust it left behind will continue to orbit the sun for centuries, slowly merging with the zodiacal light. A few atoms from that alien nucleus may fall to Earth in the form of meteoric smoke, mingling invisibly with our atmosphere, and from there, perhaps into the oceans and soils. In this way, an interstellar body that once flared brighter than expectation will leave a trace not only in telescopes, but within the planet itself. Alien carbon mingling with terrestrial life, completing a cycle of cosmic intimacy. Though it may never return, its lessons will. Every future discovery of an interstellar visitor will trace its lineage back to that incandescent encounter when every telescope on Earth turned toward the sun and saw, for the first time, the universe arriving from afar. And in that shared moment of attention, the human species glimpsed a truth older than the stars themselves, that all journeys, whether of light or of life, begin as wanderings, and that even in departure, they bind the cosmos together. When 3I Atlas disappeared beyond the reach of our most powerful telescopes, the universe did not fall silent. The space it left behind shimmered with consequences. Radiative, gravitational, intellectual. The visitor had gone, but its wake was still rippling through the solar system and through human thought. It had shown us how porous the borders between stars truly are, and how alive those borders can become when crossed by even a single fragment of alien matter. The quiet that followed its departure was filled not with absence, but with resonance. The kind that reshapes whole fields of study. By the time its last measurable photons faded from detectors, 3I Atlas had already changed the mathematics of how astronomers searched the skies. Its strange orbit had forced celestial mechanicians to reevaluate the algorithms used to filter objects that move too fast or that approach from high inclinations. Survey systems that once assumed solar system geometry were now rewritten to account for trajectories that ignore our planetary plane entirely. Engineers of all sky surveys adjusted sensors and exposure patterns so that even brief, hyperbolic apparitions could be recognized and followed. The data pipeline that processed the stream of nightly observations began to flag possible interstellar candidates automatically. In this way, the departing visitor reached forward in time. Every subsequent discovery would bear its signature in the code that made that discovery possible. The chemical fingerprint of 3I Atlas continued to deepen in meaning as laboratory analyses refined their comparisons. Meteorite researchers simulated the object's heating curve in vacuum chambers, using mixtures of ices and silicates under controlled radiation. What emerged from these experiments were new understandings of how carbon chains polymerize under sudden thermal stress. Molecules that had been frozen for eons could recombine into aromatic rings within minutes when struck by ultraviolet light and heat. Such reactions had long been proposed as early steps toward the chemistry of life. In that sense, 3I Atlas had not merely crossed a solar boundary, It had demonstrated that the seeds of complexity are hardy, and that stellar energy itself may be an agent of synthesis rather than destruction. As astronomers compared the data from this interstellar traveler to comets of native origin, a subtle theme appeared. Differences in isotopic abundance hinted at the diversity of galactic neighborhoods. The heavier nitrogen isotope, circumflex 15N, seemed more abundant in 3Y Atlas than in any local comet, suggesting formation in a colder molecular cloud where isotope fractionation was extreme. Its oxygen isotopes, by contrast, resembled those found in early solar material. This dual signature implied a protoplanetary disk that recycled matter from multiple generations of stars. For cosmochemists, it was a revelation. Proof that the galaxy's chemistry is a continuum, that stellar births overlap and blend, producing bodies whose atoms remember more than one ancestral sun. While the physical object retreated, digital replicas of it proliferated. Supercomputers modeled every stage of its evolution, from its birth in a distant disk to its slow interstellar drift and its brief interaction with our sun. In these simulations, 3I Atlas became a proxy for understanding gravitational ejection processes, how close encounters with giant planets can sling small bodies out at hyperbolic speeds. By tuning parameters, scientists could estimate the frequency of such expulsions in other systems. The results were startling. It turned out that for every planet that forms, hundreds of smaller objects may be hurled into the void. The galaxy, then, is teeming with voyagers like 3W Atlas, each carrying the mineral and chemical imprint of its birthplace. What had once seemed a singular miracle was revealed as a constant, quiet migration filling the spaces between stars. In astrophysical terms, the journey of 3Y Atlas did not end when it left the heliosphere. It entered a new medium, the local interstellar cloud, a tenuous plasma suffused with magnetic fields and charged dust. As the object's trajectory carried it outward, instruments aboard probes like Voyager and New Horizons could, for a time, measure the lingering influence of its dust stream. Subtle variations in charged particle density hinted that micron-sized grains from the comet were interacting with interstellar plasma, producing minute electromagnetic disturbances. These perturbations became natural experiments in how small bodies exchange energy with their environments. They also provided a scale model of processes that might occur in protoplanetary disks, where dust and gas interplay to create planets. Thus, even unseen, the visitor continued to educate us through the faintest of echoes. The cultural imagination of Earth followed those echoes. Writers began to treat interstellar comets as symbols of both exile and connection, messengers from a past we share but can scarcely remember. In films and literature, 3I Atlas became shorthand for the fragility of memory and the persistence of matter. A recurring motif appeared, the idea that the universe itself keeps diaries, and that each wandering body is a page from one. The scientific images, those long tales, those spectral graphs, were transformed into metaphors for migration, loss, and rediscovery. Science had delivered the facts, but art gave them human resonance, showing that knowledge and meaning are twin lights cast from the same sun. Back in the realm of research, planetary scientists began to realize that the interstellar visitor could serve as a time capsule for studying irradiation effects over cosmological spans. Its surface, darkened and chemically altered by billions of years of cosmic rays, preserved a record of the galactic environment through which it had passed. When compared to theoretical models of cosmic ray exposure, its measured surface composition helped refine the timeline of the sun's passage through different interstellar regions. In a sense, 3I Atlas acted as a sensor that had been traveling long before life arose on Earth, storing in its crust the radiation history of our galactic neighborhood. One of the great triumphs of the observational campaign came years after Perihelion, when astronomers revisited archival data from before the object's discovery. Hidden in survey images were earlier exposures showing 3Y Atlas at much greater distances than originally thought. From those faint detections, researchers reconstructed its pre-solar approach, a slow, silent glide from the outer dark, accelerating as it felt the sun's pull. The extrapolated trajectory reached back beyond the edge of the Oort cloud, far into the realm of true interstellar space. Its inbound velocity was precise enough to rule out gravitational capture. It had not been wandering near our system for long. It was a genuine newcomer, its first and only visit to our star. The realization carried a strange poignancy. This object had journeyed for millions of years only to blaze briefly and move on. But even a brief encounter can leave enduring traces. The models built from 3I Atlas's motion improved understanding of how small bodies can deliver material between stellar systems. When extrapolated across galactic timescales, these exchanges may amount to a significant transfer of volatiles and organics throughout the Milky Way. The implications for astrobiology were profound. If one interstellar object can survive ejection, drift, and stellar passage without losing all its complex molecules, then countless others may have done the same. They could act as couriers of prebiotic chemistry, scattering the ingredients of life from one world to another. The notion of panspermia, once speculative, gained a new quantitative foundation. 3I Atlas became the evidence that the galaxy itself could be a cradle for distributed genesis. The development of new mission concepts followed quickly. Space agencies began designing fast interceptor probes capable of launching on short notice to rendezvous with the next interstellar visitor. These missions would carry miniaturized laboratories able to sample dust and gas in situ, transmitting results before the object vanished again into deep space. The engineering challenge was formidable: acceleration, trajectory adjustment, communication. But the promise was irresistible. Every new design traced its inspiration directly to the brief weeks when 3I Atlas illuminated the sky. The object had proven that such missions were not fantasy, they were necessity, a natural evolution of curiosity toward action. Meanwhile, theoretical physicists found themselves intrigued by subtler aspects of the event. The hyperbolic nature of the orbit allowed for new tests of gravitational perturbation models. Minute deviations from the predicted path were compared against models of solar mass distribution and non-gravitational forces. These data refined constants used in celestial mechanics, enhancing the precision of everything from spacecraft navigation to planetary ephemerides. In this way, a fragment from another star contributed to the accuracy with which we understand our own. The departure of 3I Atlas also revitalized discussions about the long-term future of solar system science. Some thinkers proposed the creation of a permanent interstellar watch, a network of automated observatories spread across both hemispheres dedicated to detecting and tracking such wanderers. Others envisioned a database not just for scientific data, but for public engagement. An archive where each visitor's story would be told as both a scientific report and a cultural event. The consensus was clear. These crossings between stars were too precious to leave to chance observation. Humanity had to be ready to listen whenever the cosmos spoke again. Perhaps the most haunting idea to emerge from the aftermath was the realization that 3I Atlas would continue to influence the Sun, albeit imperceptibly. Each dust grain it released near perihelion absorbed solar radiation, re-emitting it as infrared heat. Though negligible on human timescales, over millions of years these tiny contributions accumulate in the zodiacal cloud, slightly modifying the way sunlight scatters through our inner system. In a literal sense, interstellar dust now forms part of the light we see at dawn and dusk. The glow that once marked the comet's path lingers, diluted but persistent, woven into the texture of our daylight. As disciplines cross-pollinated, the object's legacy deepened. Oceanographers examined whether trace isotopes from vaporized dust could eventually deposit in Earth's hydrosphere, leaving detectable chemical fingerprints. Atmospheric scientists explored how the tiniest surviving grains might seed noctilucent clouds at high altitudes. Each possibility expanded the narrative. The visitor was no longer distant, it was intimate, touching the planet not with spectacle but with subtlety. Even philosophers of time found resonance in its story. They noted that 3I Atlas's trajectory embodied the paradox of permanence through impermanence. The object's identity remained constant only because it was always changing, sublimating, venting, eroding. Its very persistence depended on loss. The metaphor echoed across disciplines, reminding humanity that transformation is the true measure of endurance. In the years that followed, other comets would come and go, but astronomers continued to measure their spectra against that of the lone interstellar emissary. None matched its exact blend of volatiles or its unusual metallic content. It remained singular, an ambassador from an epoch and environment yet to be found again. That singularity turned out to be instructive. It demonstrated that while interstellar visitors may be common in number, each carries an unrepeatable story. The cosmos, it seems, does not produce identical travelers but infinite variations on a theme. Eventually, long after human attention turned to new frontiers, the models projected 3I Atlas passing beyond the sun's gravitational reach completely. Its velocity relative to the galactic frame ensured that it would wander for billions of years before encountering another star. By then, its surface would be inert, its gases long exhausted, its minerals vitrified by cosmic rays. Yet even in that frozen state, it would continue to serve a purpose. For any civilization capable of finding it in the far future, it would be a relic, a fossil of both its own origin and of the solar system that once illuminated it. Embedded within its isotopes would be the signature of our sun, proof that for a brief moment, two stellar histories had intertwined. In this way, 3I Atlas joined the grand continuum of matter that defines the Milky Way, born of one star, marked by another, destined for endless flight. Its passing through our system was not an anomaly, but a reminder that every world is transient, every star both host and guest. When it first brightened near the sun, telescopes captured photons reflected from dust grains no wider than human hairs. When those photons reached our eyes, they carried with them the weight of stellar generations. That is the scale on which meaning exists in the universe. Light from one world illuminating another for an instant, and then moving on. Though no human will ever see 3I Atlas again, its influence persists in every field it touched, in refined models of radiation pressure, in the expanded search for extrasolar debris, in the philosophy of cosmic kinship it inspired. It taught us that the sky above is not merely a backdrop, but a living archive of exchange. Every orbit, every collision, every grain of dust participates in the slow choreography of connection. And somewhere out there, still coasting between the stars, a darkened fragment carries traces of that moment when, for a heartbeat of cosmic time, it and we shared the same sun. Long after 3I Atlas vanished into the dark between the stars, the scientific reverberations of its encounter continued to unfold like concentric circles in deep water. The data from its perihelion became a foundation upon which future generations of researchers built new frameworks for understanding not just interstellar objects, but the architecture of planetary systems across the galaxy. The encounter was finite, but the insights it released kept multiplying, evolving far beyond the object's physical presence. One of the most unexpected frontiers it opened was in the field of stellar archaeology. Astronomers realized that if interstellar comets such as 3I Atlas carried isotopic records of their home environments, then by cataloging enough of them, it might be possible to reconstruct the chemical map of the Milky Way's evolution. Each traveler could become a messenger from a different epoch and region, fragments of stars long extinct. The study of these galactic nomads thus promised to reveal the migration patterns of elements themselves, tracing how carbon, nitrogen, and iron cycle through generations of suns. 3I Atlas had, in a sense, transformed from a single object into a method, a new way of reading the memory of the cosmos. The technologies born from its observation also rippled outward into new domains. The adaptive optics and data compression algorithms refined during its brief visibility were later adapted for exoplanet imaging, allowing astronomers to glimpse fainter, more distant worlds with unprecedented clarity. Artificial intelligence models that learned to predict 3I Atlas's motion among the glare of the sun evolved into tools for tracking asteroids near Earth. Even space navigation benefited. Trajectory corrections once simulated for the comet's path became applicable to autonomous spacecraft navigating by stellar geometry. What had begun as a chase across the sky ultimately reshaped the tools with which humanity explores it. In another corner of science, biochemists turned their attention to the implications of the organic molecules detected in the comet's tail. Experiments replicated the precise thermal and ultraviolet conditions the object endured, revealing that simple interstellar compounds could indeed transform into amino acid precursors during stellar flybys. This discovery lent new weight to the idea that life's building blocks are not confined to planetary nurseries but can emerge in the open spaces between stars. 3I Atlas, by surviving a journey through such extremes, demonstrated that the boundary between lifeless and life-bearing environments might be thinner and more universal than once imagined. As centuries pass, the faint debris from that encounter will continue to drift within the solar system, mingling invisibly with the dust that paints the twilight sky. Each mote is a trace of something far older than Earth itself, a reminder that our world is constantly exchanging material with the wider galaxy. The event of Three Eye Atlas's perihelion will be remembered not as an isolated spectacle, but as the moment humanity first recognized that connection in real time, a living thread between suns. In the end, the object did not simply visit our system, it revealed that we too are travelers, carried through space by forces as vast and unending as its own journey. As the decades unfolded after Three Eye Atlas's passage, the echoes of its journey settled deep into the foundations of astronomy, altering how humanity perceived both motion and belonging in the cosmos. The event became a reference point, not just a discovery. In observatories and classrooms, it was cited as the moment the galaxy stopped feeling like a remote abstraction and began to feel alive, interconnected, dynamic, and breathing through the exchange of its smallest wanderers. One of the most remarkable developments sparked by the data was the emergence of a new discipline, comparative interstellar geology. By analyzing spectral archives and refining techniques of mineralogical reconstruction, scientists learned to distinguish between the crystalline structures born of different stellar chemistries. From this, researchers could infer the temperature ranges and oxidation states that prevailed in alien disks billions of years ago. Three Eye Atlas's unusual mineral ratios, rich in nickel but low in sulfur, became the template for understanding how dust aggregates evolve around hotter, more massive stars. In essence, the comet became the first tangible sample of a planetary system we could never visit, turning interstellar geology from speculation into science. Meanwhile, advances in remote sensing inspired by the object's fleeting brightness had broader applications. Astronomers refined light-scattering models so sensitive that they could extract information from single photons reflected off distant ice grains. The same techniques later allowed Earth-based telescopes to detect exoplanetary rings, faint atmospheric hazes, and even the glint of metallic satellites orbiting alien worlds. Every improvement traced its lineage back to the challenge of observing Three Eye Atlas when it skirted the sun's glare, a moment when necessity forged precision. Cultural reflections of the comet's passing never entirely faded either. Its story became a metaphor for the interdependence of solitude and connection, a symbol used in music, sculpture, and poetry across languages. The idea that something forged under a distant star could burn in our sunlight and move on untouched by ownership resonated with the collective imagination. Planetaria and museums built immersive exhibits that allowed visitors to follow its path from the cold interstellar dark to the blinding proximity of the sun, each step accompanied by the hum of real data converted into sound. Children who grew up beneath those domes would later become scientists, engineers, and storytellers themselves, carrying forward the vision of a universe that trades pieces of itself endlessly. In the scientific imagination, Three Eye Atlas became the prototype of the galactic messenger, a traveler whose existence linked worlds not through communication, but through shared matter. The comet's influence extended into future mission planning. Fast response probes were designed to deploy solar sails, powered by the very radiation that once illuminated it. Those sails, catching sunlight, became literal metaphors for what Three Eye Atlas had already shown symbolically: that movement, illumination, and transformation are inseparable forces. And so, though the interstellar visitor was long gone, its legacy continued to orbit within human thought. It had proven that between stars there is not emptiness, but continuity. In the space where we once imagined silence, it revealed a chorus, slow, luminous, and eternal, of worlds speaking to one another through the language of dust and light. Generations after Three Eye Atlas last reflected the sun's light, its influence still threaded through science and culture alike, an invisible current guiding inquiry toward the vast unknown. The object had come and gone in a handful of weeks, yet its echo persisted across centuries of investigation. Every discovery of a new interstellar fragment carried some trace of that first encounter, an echo of the wonder that gripped the world when humanity realized, for the first time, that the void between stars was not empty at all. The long-term archives of its spectral data continued to yield insights. As analytical instruments improved, researchers revisited the ancient recordings, applying higher resolution algorithms that could extract details once buried in noise. Within those faint signatures, they found subtleties never noticed before, variations in hydrogen-deuterium ratios across the coma, revealing gradients of formation temperature within the body's own primordial cloud. Those gradients told a story of migration inside its birth system, a young comet that had once orbited near its native star before being cast outward by gravitational upheaval. Through this reconstruction, astronomers learned not only about the comet's past, but about the dynamics of entire planetary systems, where young worlds jostle and scatter their remnants into the dark. Elsewhere, astrobiologists began studying 3I Atlas as a case study in resilience. The fact that fragile molecules endured both the cold of interstellar space and the searing heat of perihelion suggested new boundaries for habitability. Perhaps, they proposed, life's precursors could survive being flung from one star system to another, crossing unimaginable distances before finding a new cradle. This idea inspired laboratory experiments in which synthetic organic compounds were exposed to simulated cosmic conditions, shock, radiation, and freezing, and then heated to mimic a solar encounter. Many survived. It became clear that the chemistry of life was not an earthbound privilege, but a universal capacity woven into the behavior of matter itself. The comet's passage also transformed how humanity regarded time. Its journey, millions of years through the galactic plane, placed our civilization's span into humbling context. Historians of science noted how the object shifted perception. Before 3A Atlas, cosmic events were studied as phenomena. Afterward, they were experienced as correspondences. People understood that they were observing not just an object, but an emissary of cosmic chronology carrying the memory of ancient suns. The comet turned time itself into a visible thing, curving through sunlight, crossing epochs as easily as space. Even centuries later, spacecraft tracing the outer edges of the heliosphere still detected infinitesimal concentrations of dust attributed to the visitor's long-dispersed tail. Those particles had become part of the interplanetary background, a faint shimmer of alien origin forever blended into the solar fabric. Some drifted inward, seeding the upper atmosphere with microscopic minerals. A few fell as meteoric snow into polar ice, embedding an unbroken record of a stranger's passing in Earth's oldest layers. Through these legacies, scientific, symbolic, and physical, 3I Atlas continued to bind humanity to the galaxy. Its light had faded, but its lesson endured, that every world, every particle, every act of discovery is a continuation of the same cosmic dialogue begun in the silence between the stars. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on 3I Atlas achieving the impossible at perihelion? We want to hear from you. Thank you for watching and see you next time.